Alrighty, folks. So, welcome to the first lesson of chapter 11. Okay. Chapter 11 is going to have 3 lessons, and it's all going to be about this idea of the electric field. Okay, so we're going to introduce that concept here. Good news is you've seen fields before. You saw them in Physics 20. We're now just going to look at a new type of field. You saw the gravitational field in Physics 20. We're now going to look at the electric field in Physics 30. But it's actually the exact same idea. It's just instead of being associated with a gravitational force, it's associated with the electric force, what we talked about in chapter 10. All right, so we'll start out here with a little reminder of just what is a field, what does that term mean, and then we'll look at how it applies in the context of the electric force and what we've been talking about. So let's jump right in. So a field is actually a pretty straightforward idea. It's kind of a simple concept. It's one that students can sometimes struggle with a little bit because it feels a little abstract at first, but it is ultimately a simple idea that is very powerful in terms of what it allows us to analyze and predict about physical situations. Okay, so I'll start out by giving you the definition of what a field is. We'll get a little more comfortable with that idea. Okay, and then we'll see how it applies to these forces, like you already did in Physics 20 with the gravitational field. So here is what a field is. It's just a mapping of an area in terms of some quantity. So it's just, we take an area and based on some quantity that we're interested in, we assign it the correct numerical value to describe what that quantity is like at each location, right? So every point has a defined numerical value with respect to that quantity, whatever it is we're interested in. And if it's a vector quantity, if it's something like a force, which is what it will be for electric fields, it also has a defined direction. Okay, so it really is. It's just taking an area and thinking about, okay, what is this thing that we're interested in? Maybe it's a force, maybe it's a temperature or something, and giving it that correct value and mapping it out in the area. So to get a feeling for this idea, you've actually seen what is essentially a field. If you've ever watched like the morning news and they do the weather report, right? What do they often show? You might see like a map of Alberta, right? And it shows the temperatures all over the province. That is essentially a temperature field because it's showing you the value of a quantity. In this case, that quantity would be the temperature at each location in an area. It's showing you what that point would be like in terms of the quantity we're interested in. In that case, the quantity we're interested in is temperature. We'd call that a scalar field because temperature doesn't have a direction, right? Temperature is a scalar, so if we map out an area with respect to temperature, what we're kind of showing is a scalar field, a temperature field, right? And so I'll show you here, right? Have you seen a picture like this before, right? This is essentially what a field does. We've got our area here. In this case, it's, BC, Alberta, Saskatchewan, right? But notice it's just assigning numerical values. And it essentially tells you what is it like at these locations, right? And when we say what is it like, we mean in terms of the temperature. Today, we're eventually going to get to the point where we're saying, what would it be like in terms of the electric force that something would feel? But it's the same idea. It's a mapping out of an area with respect to some quantity. So you can see here, the field shows us what's the temperature in Fort McMurray today? It would be -1, right? What's it like in Kelowna? +3. In Edmonton, +2, right? And it's just showing us everywhere that they've decided to actually write it in, what would that location be like with respect to some quantity. Now, obviously, you can't label every single point, but a field is continuous, right? We could, like if we went and looked at the data from the satellites or whatever helped them make this map, right? We could say, what's the temperature like here? And add that to our field. I don't know, maybe it's 6 degrees there, right? And if we have access to the measurements that we need and the data, we could just think about what every point in space would be like with respect to this quantity. In this example, temperature. Now, if you keep watching, the next thing the news might show is a map of how fast the winds are blowing all over the province, right? And which direction they're blowing. And that's essentially a velocity field, right? It's showing you the value of a quantity, the wind velocity, at every location in an area, right? Or at least as many as they felt like labeling. They can't really do every single place because there's infinitely many, right? But however big of a picture they want to paint for you, they show you, here's what it would be like at this location in terms of velocity, how fast the wind is blowing and in which direction. Now, velocity is a vector, so this is a vector field. Let's take a look at that. I just went and pulled this image, right? This is a map showing you what the wind velocity would be like at all of these locations in Western Canada, right? So you can see they're just mapping out, okay, if you are, if you're here right now, you're going to feel a wind that's kind of blowing northwest. Not, super, super fast like these winds, but kind of fast, right? If you're down here in the United States, right, you're going to feel a wind blowing to the west pretty fast. If you're living on the coast, you're going to feel pretty strong eastern winds. So show again, right? What does a field do? It maps out an area with respect to some quantity. Okay. Now we'd need the legend here to show us how big an arrow is and what that means in terms of actual velocity in kilometers per hour, right? But that's essentially what we're looking at here. It is a velocity field. It's mapping out an area with respect to a certain quantity. In this case, velocity. A vector field, because velocity has a magnitude and a direction. And you've been working with fields all along, really, because even this, like your x and y axes, the Cartesian plane, in a sense, that is a field, right? It allows us to describe for any position we wanted here, right? For any point we wanted here, we could describe its location, right? It assigns a numerical value to every location. So now we have a way to describe where is this numerically, right? We could say it's at a x coordinate of 4, a y coordinate of 2, right? You could even think of this if this is supposed to represent, like, maybe you are standing here and we want to know where your friend is relative to you. This is kind of like a position field or a displacement field, right? Every single point here now has a well-defined numerical value in terms of some quantity. That quantity being position in this case, right? Now, no one ever really calls this a position field, but that's essentially what it is, right? Note, it checks all the boxes. It maps out an area in terms of some quantity. That quantity here just being, where is it, right? What's its position? Every point has a defined numerical value with respect to that quantity, right? We could use this to describe where that point is, or that point, or that point, or that point. Now, in Physics 20 and Physics 30, the main types of fields we're interested in, and again, a field is just a mapping out of an area with respect to some quantity, okay? For Physics 20 and 30, that quantity, for most of the fields that we're interested in, that quantity is a force. So we're mapping out an area with respect to the force that an object would feel if we put it there, right? So again, this shows you what would the temperature be like if you were standing there or there. This field shows you how hard and in which direction would the wind be blowing you if you were living here or anywhere on the map, right? What the force fields do, the electric field or the gravitational field or eventually the magnetic field, what they show you is if you were there, how much of a gravitational force or an electrical force would you be feeling and in which direction, right? So that is all these force fields do. Now, they are a very powerful tool for analyzing forces. I'm just going to quickly touch on kind of why we were so inspired by fields and why they were such a breakthrough, really, for physicists when they were trying to analyze forces. So let's start with the gravitational force. Okay, so I've drawn a little picture here. This is an apple, and it's about to fall, right? And that's interesting. Like, we all know that this apple is about to fall, right? No one's holding it there, and it's just kind of in space. So it is about to fall towards the Earth. It's about to feel a gravitational force towards the Earth that's going to cause it to accelerate downwards and be attracted to the Earth, right? And fall, we would say, okay? But this was kind of weird, right? Like, I mean, if you think back to like the time of Newton when they're analyzing these forces and stuff, gravity kind of seems to be the only force that doesn't require contact. We call it a non-contact force. In fact, gravity, that word, it was coined by Isaac Newton, and it actually, the root word there is grave, because it was kind of like this weird, spooky force that was pulling us downwards without actually anything needing to touch us, right? It's a non-contact force. Think about all, like a lot of the other forces you've studied, right? They all require you to touch it. If you want to push your bike and get it going faster, well, you've got to make contact with it, right? If you want to smack a baseball with a bat, you've got to contact the ball with the bat to change its motion, to apply a force to it. But gravity doesn't seem to need to do that, right? I mean, just think about this situation here. It's not like the Earth needs to reach up and grab the apple and pull it down. Without any contact between them, there's this force pulling them together, right? I mean, even look at the Earth and the sun. We know that gravity is what, the force of gravity is what keeps the Earth in orbit around the sun. The sun is constantly pulling the Earth towards it, right? But because of its sideways velocity, it goes fast enough that it just stays in a stable orbit, right? But that orbit wouldn't be possible without the sun pulling it in. Now, the Earth and the sun are definitely not in contact. They're separated by millions of kilometers, right? And so it's almost like, right, objects with mass kind of have an area of influence, an area of gravitational influence all around them. Now, do you see how that's starting to get towards the idea of how a field might be helpful in terms of describing that, right? Because we know that if we were to drop this apple anywhere, if we were to drop it here, it would also feel a force of gravity downwards, right? If we were to drop it here, it would also feel a force of gravity downwards. It's like the Earth has this influence over all of this space surrounding it. It has this gravitational pull. And we know that if we were to zoom out, right, we could do this for like the all around the Earth like this, right? Of course, the Earth isn't a flat line like this, right? It is a sphere. And we know this experiment works the same in Australia as it does in Canada, right? If you were to drop an apple in Australia, it would do the same thing. It would accelerate, it would feel a force of gravity towards the center of the Earth, right? And so this idea here, this kind of area of influence around the Earth, is what we would call its gravitational field. And notice how it fits all those definitions. It's just a mapping out of a quantity, okay, in the space surrounding, well, in this case, surrounding the Earth, right? What is that quantity? Well, it's the force of gravity that an object would feel if placed there, right? Give you a second to look at that picture and see, oh yeah, right? If an object were put here, we know it would feel a force of gravity towards the Earth, right? If it were put here, it would feel a force of gravity like that. If it were put here, if it were put here, or here, or here, or here. So a field allows us to start thinking about that area of influence. And so now note, the incredible thing is we don't actually need to have something there feeling a force to think about the Earth's gravitational influence there, right? Whether or not there's an object actually feeling a force, we can still talk about the force it would feel if placed there, okay? And to start assigning numbers to it, because a field has a magnitude, and in the case of a vector field, it also has a direction, right? Well, we can say, okay, you know from Physics 20 that you can calculate the force of gravity something feels by taking its mass and multiplying it by acceleration due to gravity, right? And if you do this experiment with, a 1 kilogram mass near the surface of the Earth, it will feel, if let's say this apple is 1 kilogram, it'll be 1 kilogram times 9.81 meters per second squared, right? So it will feel 9.81 newtons of force. If you were to then take that same experiment, take that 1 kilogram apple and do the same experiment over here, well, even if we don't actually move the apple there, we can think about the fact that, well, nothing's really changed here. It would feel a force of gravity of 9.81 newtons, right? And so you can start to see how we're mapping out the area around the Earth with respect to some quantity, right? If I do it over here with a 1 kilogram apple, it will feel 9.81 newtons of force. But then you start to think about it and you realize, well, there's a problem with that. Because the apple, sure, if it's 1 kilogram, it'll feel 9.81 newtons of force. But what if it were something bigger? What if it were, a watermelon? And this watermelon has 2 kilograms of mass instead of 1 kilogram. So now we have to take that watermelon, it would feel twice as much gravitational force as the 1 kilogram apple. 1 kilogram is a very heavy apple, I guess. But just for the sake of the numbers, right? It would feel twice as much gravitational force now because it's got twice the mass, right? So instead of only feeling 9.81 newtons of force here, it would feel double that, 19.62 newtons, right? And if we repeat it over here, it would feel 19.62 newtons. Okay, so that almost kind of gives us a problem with the gravitational field because we say, oh yeah, but like we're trying to think about the Earth's gravitational influence and the force it would exert on an object if placed there, but if the object has different masses, it's going to feel a totally different force, right? So there's an easy way to get around that we talked about in Physics 20. We just say, okay, sure, we don't necessarily know what object we're thinking about feeling a force there, and maybe we're not even thinking about a force there at all. In fact, we're just thinking about what the Earth's gravitational influence would be like at that location. So the easy fix is just say, how many newtons of force would it feel for every kilogram of mass it has, right? And then there we go. Now we can say, and we do say this, right, that near the surface of the Earth, the gravitational field strength is 9.81 newtons per kilogram. And then we know, okay, so if you have 1 kilogram of mass, you'll just feel that many newtons of force. If you have 2 kilograms of mass, you'll feel twice as much, right? If you have half a kilogram of mass, you'll feel half that much of a gravitational force because of the Earth's gravitational influence at that location in space. And there we go. That's how we get around this. So the gravitational field, which by the way is the same, you might recall from Physics 20, it is g, okay, it's acceleration due to gravity, but it's also the gravitational field strength. So the gravitational field strength is, and you can even see it from rearranging this equation, right? It's just measured in newtons per kilogram. And so now what we can do, whether there's a watermelon there or an apple or whatever, we can say that the Earth's gravitational field strength is 9.81 newtons per kilogram. It's 9.81 newtons per kilogram there. It's 9.81 newtons per kilogram there, right? And now notice, it doesn't matter what we're thinking about putting there. We're generalizing to say, all right, yeah, the Earth has a gravitational influence here. How strong is it? Well, it's going to pull on you towards it with 9.81 newtons of force for every kilogram of mass that you have, right? And there we go. Look what we've now done. We've mapped out an area with respect to some quantity. In this case, the quantity is the force, the gravitational force that you would feel for every kilogram of mass that you have because of the Earth's gravitational influence. Now again, you know from Physics 20 that it's not 9.81 way up here, right? It gets weaker as we get further from the Earth, according to this equation here, right? It gets weaker the further away we get, but we can still think about and even calculate what it would be like, right? Maybe up here it's more like, I don't know, 5.2 newtons per kilogram, right? And look what we're doing. We're mapping out the Earth's gravitational influence, mapping out the force of gravity you would feel because of the Earth's gravitational pull at all of these different locations. And this was huge for physicists because now they had a way to analyze and contextualize and map out this kind of weird force that seemed to not require contact. We map out how strong the Earth's gravitational influence is. And notice it's just a field. Just like this tells you, how fast and in which direction the wind would be blowing on you if you were in Kelowna, right? This tells you how strong would Earth's gravitational, how strong would the force of gravity that you felt towards the Earth be if you were there, or there, or there, or there, for every kilogram of mass that you have. And so that's what these force fields map out, right? All fields just map out an area with respect to some quantity. For force fields, like gravitational field you studied in Physics 20, or the electric field we're going to study now in Physics 30, that quantity they're mapping out is the force that another object would feel if it were placed at a given point. And again, like we just saw, right, it's important to note that nothing actually needs to be at that point feeling a force. The field exists either way, right? Earth has a gravitational influence here. Even if there's nothing there, we can still think about the force that an object would feel if placed there for every kilogram of mass that it has, okay? So it asks us this question: do you think that the fields associated with forces are vector fields or scalar fields? Well, they map out the force that an object would feel, right? So do forces have directions? Are forces vectors or scalars? Forces are vectors, right? I mean, you can even tell from the fact we're representing it with arrows, right? A force has a direction. So these are definitely vector fields, right? Because they're describing how a vector looks in certain areas, right? Or I guess how that force would look if there was an object actually placed there to feel it, right? The same way this is a vector field because it's telling us about what the velocity of vector would look like at different places. These force fields, gravitational fields or electric fields, are vector fields because they're telling us about what the force would be like if you were there or if an object were there. Okay, so here's just a quick recap of the stuff we really just talked about with the gravitational field, but here in the notes typed out. So the Earth has a gravitational influence even if nothing is there falling, right? We say that the Earth generates a gravitational field, right? Any object with mass, you know from Physics 20, generates a gravitational field. It has a gravitational influence. And at any point around an object with mass, right, any point at all, we can imagine the gravitational force another object with mass would feel if it were placed there. Even if we don't actually have something to put there, we can still think about the force that an object with mass would feel if we placed it there for every kilogram of mass that it has, right? So it will feel this many newtons per kilogram of mass. That's the gravitational field, newtons per kilogram. So the gravitational field defines how big and in what direction the force would be at that point. Now with gravity, it's always towards the source of the field, right? Gravity never pushes things apart, it only ever pulls them together. Gravity is only an attractive force, right? And so this field exists all around the source mass, right? And so by kind of considering this, force that's waiting to happen or this force that could be if we put something there to feel it, all around it, what we do is we're mapping out the source mass's gravitational field. And what that actually looks like visually is this picture that we drew earlier, right? Shows us what the gravitational force an object would be like for every kilogram of mass that it has at every location in the Earth's area of influence, so to speak, right? And of course, there's a numerical value associated with it. So for example, if we say that at that location, the strength of the gravitational field generated by the Earth is, I don't know, how about 8.9 newtons per kilogram? All that means is that if you put 1 kilogram of mass there, it would feel 8.9 newtons of gravitational force towards the Earth. Okay. Now, if you're wondering why are we talking so much about the gravitational field, right? I thought we were talking about electricity now in Physics 30. Well, it's because if you remind yourself of these ideas from the gravitational field, you'll see when we start talking about here now electric fields, it's the exact same idea. It's just instead of describing the gravitational force an object would feel if placed there for every kilogram of mass that it has, we're talking about the electric force something would feel if placed in that field for every coulomb of charge that it has. So let's jump in, right? And really notice the similarities between the bullet points here, right? The Earth has mass, so it generates a gravitational field. Well, anything with electric charge generates an electric field, okay? So charges generate electric fields. And the field that they generate is there even if they're not currently attracting or repelling something, right? The Earth has this gravitational influence even if there's not something there right now feeling some force. We can still think about the force it would feel if it were there. Same idea with the electric field. A proton generates an electric field, for example, right? And we know that if I put another charged object here, it will feel a force, right? So what we're thinking about there is the field that surrounds the proton, right? And if we can quantify that, we can start talking about, okay, how many newtons of force would something feel if I put it there, even though there might not be something there now, right? And so at any point around a charged object, we can imagine the electric force another charged object would feel if placed there for every 1 coulomb of charge that it has, right? Gravity acts on things with mass. So we think about how many newtons of force it would feel for every kilogram of mass it has when talking about the gravitational field. When talking about the electric field, well, electric forces, we know, affect things with charge. So we think about, all right, how many newtons of force would it feel for every coulomb of charge that it has? And by doing that, we would be mapping out the electric field generated by the source charge. I'm going to hold off on drawing directions here because we're going to have to think a little bit more about the direction of the electric field, okay? Actually, I'll show you what it looks like. You're going to be like, why does it look like that? We'll come back to that later, but just to give you the idea that it is the same idea, right? Okay, we're thinking about what kind would it feel a force, right? And we know charges would feel a force if they were around another charged object. So this is actually a visualization of the electric field around a proton. I'll get into in a moment here why these arrows are pointed away. But I just want to show you, look how similar these ideas are, right? It's the same thing. How many newtons of force would it feel for every kilogram of mass it has because of the Earth's gravitational field? How many newtons of electric force would it feel for every coulomb of charge that it has because of the proton's electric field? All right, so as we keep mentioning, right, in Physics 20, you studied gravitational fields, okay? We're taking a look at the equations here now, and look, the similarities just continue, right? Look how similar the equations are between electric field interactions, forces and fields for electricity, right, and for gravity, right? Look at them, KQQ over R squared, GMM over R squared, right? The electric force acting on an object, this is just Coulomb's law, right, is the electrical constant or Coulomb's constant, and it depends on their charges and how far apart they are squared, right? For gravity, it depends on their masses and how far apart they are squared, and we use the gravitational constant, right? Look at this one here. Just wanted to pause there and draw a quick diagram to help visualize here, okay? So again, like look at this equation here, right? The electric field is equal to, one way to calculate it, the electric force acting on a charge that is placed in that field, right? So there's two equations for electric field. Notice they're very similar to the two equations for gravitational field you did in Physics 20, right? Again, I drew those diagrams again. So one way we could do it, because remember, all the electric field is telling us is how many newtons of force would a charge feel if we put it there for every coulomb of charge that it has, right? So one way to do that is to actually put a charge there, figure out what force it feels, and then divide by how many coulombs of charge it had, right? So if it felt 10 newtons of force and it had 1 coulomb of charge, the electric field there would be 10 newtons per coulomb, right? But if it felt 20 newtons of force and this had 2 coulombs of charge, we would say, well, 20 over 10, the electric field still works out to be 10 newtons per coulomb, right? So what's the difference between the two equations? It's really just based on, well, what do you know about the situation, right? So in this one, this is what we would call the source charge. And it's the source charge because it's the source of this field that we're interested in, right? This also generates an electric field, but in this example here, we're interested in what does this generate? At this location, what does the electric field being created by this blue one look like? How strong is it? How many newtons of force would a test charge feel if placed here for every coulomb of charge that it has, right? So look at the equation. It makes a ton of sense. If we knew the force that it felt and we knew how many coulombs of charge this test charge had, well, there we go. We can say, well, when I put a test charge here, it feels this much force, so we can work backwards and figure out, all right, this must be generating an electric field that is however many newtons per coulomb, right? To connect it back to the gravitational field, okay, this equation is the equivalent for gravity, right? So again, it's just based on what you know. If we're interested in the gravitational field strength of the Earth here, where this satellite is, right? One way we could figure that out is to say, okay, well, how big is the force of gravity that this satellite is feeling? And then divide it by the satellite's mass, right? Because again, the gravitational field tells us how many newtons of gravitational force would an object feel for every kilogram of mass that it has if placed here, because of the Earth's gravitational influence, right? So if we take an actual mass, put it there, figure out the gravitational force it feels, well, then we just need to divide by its mass to know how many newtons it felt per kilogram, right? And so that's that set of equations there. But then there's this other one that is based on not actually having to put something there at all, just doing it based on the properties of the source itself, whether that's the source of a gravitational field, so a charge, or, sorry, I said that backwards, the source of a gravitational field, so a mass, or the source of an electric field, so a charge. So in this one, notice it's just kq source over r squared. So q source, that means the charge of the thing that's actually creating the field we're interested in, right? So in this one, it's the test charge, we call it. It's a charge that we actually did put into the field, saw how much force it felt, and then divided by its charge to figure out how many newtons it felt per coulomb of charge that it had, right? Here, notice this is literally, it's just a point in space. There could be something there or there could not. We don't need another charge to be there if we know enough information for this equation to work, right? This is just, if I want to know what is the electric field here, I could just know how far it is from the source charge and the source charge's magnitude itself, right? If I know those two things, I can calculate what the electric field would be like there, for example, right? So do you see the difference between the two equations? Both are calculating the same thing. Both of these are calculating the electric field strength of this source charge, okay? The electric field it generates at a given location. One just does it for when you actually do have another charge there feeling a force and you know how big that force is. One does it when you don't have that, but you do know how far away you are from it and you know how big the charge is that's generating the source, right? Again, to connect it back to gravity, the similar situation would be, okay, maybe you don't have a satellite there feeling a force, or you don't know anyway, right? But you do know the mass of the thing that's creating the field you're interested in. In this case, if we wanted to know how strong is the gravitational field generated by the Earth here, all we would need to know is, well, what's the mass of the Earth, the thing generating the gravitational field we're interested in, and how far is that point in space from the Earth's center, right? So it's the same, it's the same idea, just for gravity versus electricity. Very similar concepts though. Okay, so that's what's being emphasized here. The field, this is how we could calculate the field based on a force that's felt by a test object, right? That's what this equation is set up to work with. It's set up to work with some other charge actually felt a force, and we know that force and we know the charge of the object that felt it. Whereas this one is set up to work just based on knowing properties of the thing that is creating the field that we're interested in, right? So maybe we know the source charge's charge and we know how far away the point that we want to find the field strength at is from our source charge. Okay, so it asks us here then, what are the units of electric field? Now, honestly, we know we can use the equation to tell us, but we can also kind of just think about this one a little bit, can't we? Right? It's telling us how many newtons of force a test charge would feel for every coulomb of charge that it has if placed at a given location, right? So that kind of suggests that, well, it's telling us how much force per unit of charge, right? Well, force is measured in newtons, charge is measured in coulombs. So wouldn't newtons per coulomb? That sounds like a reasonable estimate just based on what we know about the electric field. Let's see what the equations tell us though, right? We have two equations. Let's do this one first. Okay, so using the one for when we've actually got another test charge feeling an actual force, right? Well, what do we measure forces in? Newtons, right? What do we measure charge in? Coulombs. So electric field is measured in newtons per coulomb, like we kind of predicted, right? Does it work with the other equation, the one for when you maybe don't actually have a test charge there feeling a force, or at least you don't know anything about that, but you do know the charge of the thing creating the field, and you do know how far the point you're interested in is from that charge? Will that equation give us the same units? Let's find out. So it's kq over r squared. We know k, Coulomb's constant, is measured in Newton meters squared per coulomb squared, right? And if you've forgotten that, it's on the back of your formula sheet. We know that charge, q, is measured in coulombs. And we know that distances, like r here, are measured in meters. And those meters are being squared. So if you take a look here, look at this. Meters squared are getting divided by meters squared. And then we have coulombs that are getting multiplied by 1 over coulombs squared. So one of those coulombs can cancel, and sure enough, same units. Electric field is measured in newtons per coulomb. Now that makes a ton of sense, right? Because it's just saying, yeah, if an object were placed here, it would feel an electric force. That electric force depends on how many coulombs of charge it has, but we can still generalize it to say this many newtons of electric force per coulomb of charge we were to place at that location. And that point really gets hammered home when we take this equation and we rearrange it for the force, just to really demonstrate what the electric field is telling us, what that value tells us, right? Because look, the electric field tells us how many newtons of force something will feel for every coulomb of charge it has. And so if we multiply by the number of coulombs of charge that that test object has, we get the force it feels, right? Just for example, if there is a 10 Newton per coulomb electric field and we put a 1 coulomb charge there, it will feel 10 newtons of force, right? The electric field there was 10 newtons per coulomb. And it still works if we put a 2 coulomb charge there, right? If there is a 10 Newton per coulomb charge, and instead of putting a 1 coulomb charge there, we put something with 2 coulombs of charge. Well, it still works. It's going to feel more force because it has more charge. But the electric field was still 10 newtons per coulomb. So a 2 coulomb charge feels 20 newtons of force if placed into a 10 Newton per coulomb electric field. And one more thing that's worth pointing out here, if we take that same one we were just talking about, so the electric force, if we rearrange this one, right, we can find that the electric force acting on an object will be equal to its charge times the electric field that it's currently in. Now, if I then take this equation, which tells me the strength of the electric field based on the properties of the source charge, what I will actually get, well, I won't spoil it. Let's see. So if I take this and I say, okay, great, but the electric field is just kq over r squared, right? Q being the charge that's creating the electric field, r being how far we are from that charge, okay? Well, look, if I take this and I put it in here, do you see where this is headed? Q times kq over r squared. And if we simplify that a bit, actually multiply the q into that, expression there, we get kq over r squared, which is just Coulomb's law, right? Putting those two equations together essentially gives us Coulomb's law, right? The force that will be acting on a charge will be equal to the product of the two charges times Coulomb's constant divided by r squared. And we can see that that's exactly what this equation is kind of saying here, right? The electric field generated by a charge is kq over r squared at a given location from a charge q, right? And if there's another charge there, we can just multiply by that thing's charge to figure out what the actual force will be acting on it. Cool, right? So now here they all are on your formula sheet, okay? Under electricity and magnetism, okay, there's Coulomb's law. That's from, well, we won't stop using it or anything, but that was introduced in chapter 10. But here are the two new equations, the one for calculating the electric field when you know the charge that's creating that field and how far away from it you are, right? And also the one for calculating the electric field if you know the force that's acting on another charge that's actually in the field and therefore feeling a force, right? Because that's what electric fields do. They can cause another charge to feel a force. So if there actually is another charge feeling a force, we can use that information to figure out the electric field as well, okay? So important to note, your formula sheet doesn't tell you. It doesn't say Q source, Q test. I put that in the notes when we're introducing it so we can get the feeling for it, okay? But again, like when you think about it, it'll make sense, right? Like, again, if something's actually feeling a force, you got to ask yourself, this is why it's important to understand in physics and not memorize, right? If you understand what the electric field is talking about, it's saying the force another charge could feel if placed there, well, then this one only really makes sense. If it's newtons per coulomb, that's the charge that was feeling the force as a result of being placed in that electric field, right? This one is just talking about how far are you away from a charge that's generating the electric field. Okay, let's try out an example here. I know I haven't talked about electric field direction. That is coming up, okay? But I just want to get the hang of actually trying this out. So it tells us that a pith ball has a charge of 12 millicoulombs and is placed 10 centimeters from a charged ball, which has a charge of 2 coulombs. Calculate A, the magnitude of the electric force that's felt by the pith ball, and B, the magnitude of the electric field generated by the charged ball at the location of the pith ball. Two different ways. Okay, so again, important to remember, forces and fields are not the same thing, right? That is a common student mistake at first. They say, okay, so a force field is just a force, I guess. Not quite, right? The field is related to the force. It's telling us what force would something feel if placed here per coulomb of charge that it has. Okay, now remember, the field is there either way, right? Even if there's actually nothing here at all, there is an electric field being generated by this. Remember, it's all about what force would something feel if placed there. There might be something there feeling a force, and there might not be. Either way, the field is just a way of thinking about how many newtons of force would something feel if placed there for every coulomb of charge that it has. Okay, so be careful. Forces and fields are not interchangeable. Okay, but all right, A is actually just a chapter 10 question. This is just a Coulomb's law one, right? We're given two charges, the distance between them, and we want to calculate, sorry, got something in my throat there. We want to calculate the force that's being felt between them. So let's draw a picture like we normally would. All right, so we got our 12 millicoulomb pith ball. I'm going to call that 1 just for the sake of the calculations and giving labels to everything. And our 2 coulomb charged ball, I'm going to call that object 2 just for the sake of labeling. And the distance between them is 10 centimeters, right? Which don't forget to convert to meters, divide by 100, 0.1 meters. Okay, so like I said, this is just a Coulomb's law, right? We know the two charges. We know how far apart they are, so we can just KQQ over R squared this. We can just say that the electrostatic force between them will be that, right? And then putting in our numbers. Okay, same old K, right? Coulomb's constant. It's a constant. It never changes. Just kind of governs how strong the electrostatic force is in our universe, okay? But putting those in and calculating, I got 2.1576 times 10 to the power of 10 newtons. That would be the electric force between them. That is a really big number, but remember, the electric force is really strong, right? So it's actually not that surprising. And honestly, 2 coulombs is a lot of charge. Remember, 1 electron or 1 proton has 1.6 times 10 to the negative 19 coulombs of charge. So this is actually a lot of charge, so a very strong electric force is actually not as surprising as that seems. Now, it just asked for the magnitude, so, I mean, we could give the direction if we wanted. Well, I mean, we couldn't actually, because we don't know if this is actually on the left. It didn't say that. I just put it on the left for my diagram. But we do know that at the very least that it would it be attractive or repulsive? Would this be an attractive force pulling them together or repulsive pushing them away? It would be repulsive, right? They're both positive. So we could at least say that if we wanted. Although it did just ask for the magnitude, so we don't need to sweat it too much. All right, now B is where we're actually thinking chapter 11 stuff. Now we want to actually calculate the electric field being generated by the charged ball at the location of the pith ball. So that's very important, right? what is the thing that's making the field we're interested in? Because these both have charge. So they do both generate an electric field, right? In fact, it's the fact that they both create an electric field that leads to the force. Two things that both create electric fields, those fields will interact, and it's that action that actually gives rise to the force itself, okay? So this is creating an electric field, and this is creating an electric field because they both have charge. Just like you learned in Physics 20, right? This is generating a gravitational field because it has mass, but so is this. This is also generating a gravitational field. It has mass, okay? So important to understand what is the source of the electric field that we're interested in at the moment. Well, it says the electric field generated by the charged ball. So we're interested in this as the source, right? We're saying, okay, what electric field is this creating over here? Because it says at the location of the pith ball. Of course, it's generating an electric field all around it, but we're interested in what is its electric field like here. Now, there's two ways we could go at this because we actually have a lot of information. We do have another charge there. And we know that charge is charge, and we just figured out the force that it's feeling because of this thing, right? So we could say, we could do this. The electric field there will be equal to the force felt by another charge divided by the charge of that charge that felt the force, right? But we also have enough information. We know how far away we are from the source of the field, and we know the magnitude of the source charge's charge. So we could also use this, K times the charge that's creating the field we're interested in, divided by how far away the location we're interested in is from that charge. Essentially, this one, we don't even need to know anything about that, right? We're essentially ignoring that and just saying, okay, based on the properties of this thing, what would its electric field be like there? Whether or not there's something there is no longer an issue because of the magic of fields, right? So let's do it both ways. Okay, I'll do it this way first. The electric field is equal to the force felt by another charge when placed there, okay? So we've calculated that that charge is going to feel a force of 2.1576 times 10 to the 10th power newtons. Now, question for you. What charge am I about to divide by? Should I divide by 12 millicoulombs or should I divide by 2 coulombs? I need to divide by 12 millicoulombs for this equation, right? Again, don't forget, the electric field just says how many newtons of force would something feel if placed here per coulomb of charge because of this thing's field, because that's the field we're interested in calculating. So we know how many coulombs of charge this thing had, and we know the force it felt because of this thing's field. So take that many newtons and divide it by the test charge's charge, and we can figure out how many newtons it felt per coulomb of charge, and therefore the electric field strength there. So putting that into my calculator, I got 1.798 times 10 to the 12th power, and what would my units be? Newtons per coulomb, right? Again, just saying, if a 12 millicoulomb charge felt that much force, well, it must be feeling this many newtons for every coulomb of charge it has, right? And now we've worked out the electric field strength there, based on the force felt by a test charge that was actually placed there, right? So this is the number of newtons a 1 coulomb test charge would feel if placed there, which is essentially the definition of the electric field. Okay, now I should be putting magnitude signs around here because we're not talking about direction. We'll talk about direction in a moment after this, okay? But I should do significant digits as well. Looks like we only get 2. So I'll round this to 1.8 times 10 to the 12th power newtons per coulomb. All right. Now, we should get the same result if we do this, right? We can't calculate the same thing 2 different ways and get 2 different answers if both of them are supposed to be correct. So let's test it out with this one now that's based not on an actual force felt by a charge placed there, but just based on how big is the charge creating the field and how far is the location we're interested in from that source charge. So essentially, like I said, we can ignore this if we have this information as well. Okay, let's try that one out. Okay, so Now we can say, all right, it's still the same K. It's still 8.99 times 10 to the 9 Newton meters squared per Coulomb squared, okay? But now the charge we need to use is the charge of the thing creating the field we're interested in, right? That's what this equation is for, when you know that information, okay? And now really what we're doing is we're just saying, who cares about this point, right? At this location, right? Not this actual physical object that is a charge, but just at this location. That's all we need to know is how far is that place from the thing creating the electric field, right? So I'll just say the source of the charge, the thing that's generating the field we're interested in, is 2 coulombs, and we are 0.1 meters away from it. So we can figure out how strong its electric field would be there, right? That's kind of the whole point of fields, is to be able to think about what the force would be like because of this thing, whether or not there's actually something there to feel a force, okay? So putting that into my calculator, I got that the electric field there would be, not too surprisingly, also 1.798 times 10 to the 12 newtons per coulomb. Or to two significant digits, 1.8 times 10 to the 12 newtons per coulomb. Okay, now the purpose of this is to show you that it is the same thing. We are calculating the electric field created by this charge here. There's just two ways to do it, right? We could do it based on the force that's actually felt by a test charge, or we could do it just based purely on the properties of the source of the field alone and how far we are from it. Now, typically you will not have all of this information. You won't have enough information to do it both ways, right? You might know this stuff or this stuff, but it's pretty rare you'll know both. But this was an introductory example to get the idea of what is the difference between this equation and this equation. They're not different in terms of what we're talking about in calculating. They're just different in terms of what do we know in order to calculate that, right? And how are we like measuring it? What do we know about the situation? Do we know the charge of the thing that's creating the field? Or do we know the charge of the thing that's feeling a force because of the field? Okay? So go ahead and try this one out. And this one's good practice for letting you think about, okay, what do I know here? Do I know about the charge that's creating the field, right? And how far we are from it? Or do I know about the amount of charge of something that's actually feeling a force because of the field that I'm trying to calculate? Okay, this is you're going to have to manipulate the equation for this one, okay? But you know how to do that. So go ahead, give that one a shot. And then, as always, you can try out a couple other practice questions, although honestly, I believe from your practice assignment, not a ton of them are going to be doable just yet because we still need to talk about the direction of the electric field. But at the very least, do this one while it's fresh in your brain, and then we'll move on and we'll finally talk about the field direction. How do we come up with the electric field's direction? Because it is a vector. All right, so in Physics 20, you learned that the direction of the gravitational field, right? What direction is this vector of the gravitational field? Well, it's just in the same direction that the mass would actually feel the gravitational force, right? And this was always pretty simple because a test mass will always feel a force towards the source mass, right? I mean, it's easy to think about gravitational field direction because yeah, if I put an object here, it's going to feel pulled towards the Earth. If I put it here, the force of gravity from the Earth's field will be towards the Earth, right? Gravity is always attractive. So it was easy to think about what direction the field would be. It's also just towards the source of the field, okay? Now, again, remember, the test mass isn't necessarily a real mass, right? We're just thinking about a 1 kilogram mass. If we put it there, how many newtons of force would it feel? That's kind of the entire point of a field. It lets us think about this area of influence and what it would be like for a mass if placed there. We're not saying there's actually a 1 kilogram mass there, but we can still think about what a 1 kilogram mass would feel for in terms of the gravitational force acting on it, okay? So it just lets us think about the force that would be felt by a real 1 kilogram mass. Don't forget, fields exist even if nothing is there to feel a force. Now, this is the reason that electric fields are not quite so simple. And it's because, again, we know that the electric force can be attractive or repulsive, depending on what type of charges are involved, right? That was never the case with gravity. There's no type of mass that can repel other mass, right? It always attracts. Gravity pulls things together. It never pushes them apart. And so now the fact that our test charge is kind of just hypothetical, right? We're kind of just thinking about what would it be like for a 1 coulomb charge if we put it here? What force would a 1 coulomb charge feel if it was placed here? That kind of becomes a problem because that's not enough information now to talk about what the force would be, right? Because you would have to follow up and say, well, is it a positive 1 coulomb charge or is it a negative 1 coulomb charge, right? If I have, let's say, a proton that's generating an electric field, and we want to know what is the electric field generated by this proton like here, right? Well, we know that the electric field is essentially saying what force would a 1 coulomb charge feel if placed here. But force is a vector. And so the problem becomes, well, if I put a 1 coulomb positive charge there, it will feel a force to the right because it will be repelled by this positive, right? But if I put a 1 coulomb negative charge there, it'll feel a force to the left because it'll be attracted to this positive proton, right? And so that's kind of the problem we had with the electric field. How can we define the direction of the field if two different types of test charges, positive versus negative, would feel forces in opposite directions, right? That's the problem we're kind of facing. Right? And I mean, same problem still if it's a negative source charge here, right? Because again, if we want to think about the electric field there, well, we know it's saying how many newtons of force would a 1 coulomb charge feel if placed there. But again, if it's a positive charge, now it will feel a force to the left of attraction. And if it's a negative 1 coulomb charge, it will feel a force to the right. And so the solution we came up with to this problem was essentially just, okay, well, let's all agree to think positive. And what I mean by that is, like, we arbitrarily had to agree on the type of charge that we imagine on that test charge when we're thinking about the field direction. And we decided that we'll all just agree so that we can talk about the direction of the field without, having to explain ourselves a million times and say, okay, well, if it were positive, it would do this, but if it were negative, it would do this. We just agreed to say that whenever we're talking about the direction of the electric field, we define it as the direction that a positive test charge would feel a force. So we just imagine when we say, what is the electric field like here? We just agree to say that the electric field direction would be to the left, because that is how a positive test charge would feel a force. Now notice that means if we actually put a negative charge there, it's going to feel a force to the right. That doesn't change the fact that the electric field would still be defined as to the left, because for electric field, we agree to think about what a positive test charge would do. So all that means is that positive test charges feel forces in the same direction as the electric field, while negative test charges actually feel a force in the opposite direction of the electric field. Because remember, the whole point of this electric field is just to think about what is it like here, right? What kind of force would happen here? And so getting too bogged down in, it's different for a positive versus a negative kind of defeats the purpose, right? And we just say, all right, well, if it's a negative that we actually put there, it'll feel a force in the opposite direction of the electric field, okay? So do you remember that picture I drew earlier where I said this would be the electric field around a positive object, okay? And I said, I'll get to why they're pointing away from the positive later, right? Do you see now why? Because we ask ourselves, what would a positive 1 coulomb charge feel if placed there? Well, a positive would repel it. A positive test charge placed here would feel a force away from this positive charge that is generating the field we're interested in. Does this picture make sense to you then, right? If it's a negative source that's generating the electric field we're talking about, the electric field actually goes towards it. Well, again, think about it. The electric field's a way of thinking about the force an object would feel if placed in this area, right? This area of influence, okay? And since we had to pick one to think about, and we picked positives when we imagined placing a 1 coulomb charge there, right? Yes, a 1 coulomb charge would be attracted towards this negative if it were a positive test charge. So that's what we imagine, right? We say, okay, what kind of force would a positive 1 coulomb test charge feel if placed there? Well, it would go towards the negative, right? Or there. It would feel pushed towards the negative. Or there. Towards. There. Towards. Okay? Now, keep all in mind, we might actually take a negative charge and put it there. There's nothing wrong with actually taking, an electron and putting it here. And a negative charge feels a force in the opposite direction of the electric field. That's just a consequence of how we've agreed to define the electric field direction, right? So a negative test charge would feel attracted towards a positive. Opposites attract, right? A positive test charge would feel pushed away from it in the same direction as the electric field. A negative test charge would go towards it, okay, in the opposite direction of the electric field. All right, so that is how we have to define electric field direction. Two different types of charges would feel forces in opposite directions. So instead of getting too bogged down in that, we said, okay, but the whole point of the field is to talk about what the force would be like, whether there's something there or not. So let's just agree to think about a positive, and then we'll know if there's actually a negative there, it feels a force in the opposite direction as the field direction. All right, so now that we've talked about electric field a little bit, okay, what it means, and we've talked about its direction, let's just kind of mess around with this thing a little bit and look at it here, okay? So what I've got here is a positive charge. It's a charge, so it creates an electric field, right? And this thing here, this could be our test charge, okay? So what we're gonna do is think about, okay, what force would it feel there? And it shows us, right? It shows us that, okay, if this were a positive test charge, it would feel a force pushing it away from this positive source charge that we've got in the middle there, right? As we get closer, that force would get stronger. We knew that. As we get further, that force would get weaker, right? And we can look at that force all around, and we can think about what the electric force would be like all around our positive test charge. And all the field is doing is essentially mapping that out everywhere, right? Assigning a value saying it would feel this many newtons of force for every coulomb of charge that it has. And so to visualize that, we could do this. So there is a diagram of the electric field. Now, we don't often represent it like this. This is just how the simulation's choosing to represent it with many different arrows. Like you saw there, we usually just use like a single continuous arrows, but this gives another visual, right? And notice all it's showing, right, is the force that would be on our test charge, the direction, and the magnitude. They're showing the magnitude getting weaker out here by making those arrows more faded, right? As we get closer, it gets stronger. Notice it's just mapping out what the force would be like on our positive test charge all over the place. So again, there might be an object here, or there might not be, but we can still think about the force an object would feel there. And that's what the field does. It just maps out the space in terms of a quantity, right? Now, if I take that positive and I replace it now with a negative, make a prediction. What's the field going to look like? Right. Now it's pointed towards this negative source charge. And that makes sense because we know, again, the field is talking about the electric force a test charge would feel if placed at a given location. And we agree to think about the force that a positive test charge would feel, right, for every coulomb of charge that it has, so that we can just agree on a way to think about the direction of this vector field, the electric field, right? But sure enough, right, look, all it's doing is showing us what would the force be like here or here. The electric field's just showing us all of the possible places we could be thinking about, right? Obviously, we can't draw all of them literally because there's infinitely many, right? But a mapping out of what the general electric force would be for a positive 1 coulomb test charge placed at any of these locations. And these can start to get interesting, right? There could be multiple electric fields from multiple charges interacting at a given point in space, right? So for example, here, this positive test charge is generating an electric field. this negative test charge is generating its own electric field that looks like that. And if they're both in this area, both in this space, those two electric fields that are unique to them can combine, right? It's not that we've changed each individual one's electric field, but their combination, their vectors, they add like any other vector. Their combination can change the overall electric field at a given location. So I'm just going to show you, if I just have the positive one, right, and we say, let's say we test that place there. The electric field there is kind of up and to the right, like we would expect, right? A positive test charge would feel pushed away from this positive source. Okay, now let me take the positive out and put the negative in. And I'm going to put this at roughly the same location, and we see it's down and to the right, right? So we have an electric field from the negative one here that is down and to the right, and from the positive one here that is up and to the right. So if you add those two vectors together, up and to the right and down and to the right, what do you get? Whoops. You get just to the right, right? Because up and to the right plus down and to the right, the up and the down parts kind of cancel out. So overall, at this location right here, the electric field is kind of just to the right. And sure enough, that checks out, right? It would feel repelled to the right by the positive source charge if it were positive, but also attracted to the right by the negative. Okay, it would be repelled upward by the positive, and it would be attracted downward by the negative if it were a positive test charge, which is what we agree to imagine when we think about the electric field direction. Okay, and we can do lots of cool combinations with these, right? If I put a positive test charge here, so two positives, look at the electric field kind of in the middle, right? From this one, it's feeling pushed up and to the right. From this one, it's feeling pushed up and to the left. If we go right in the middle here, the right and the left components of that electric field cancel each other out. So here the electric field is straight up. Here it's straight down. Okay, you can start making some cool patterns with these if you play around with them. These simulations, by the way, they're always posted in the agendas. I do encourage you to go mess around with them, okay? But again, look, all this is showing us is if I were to take a positive 1 Coulomb test charge and put it here, it would feel a force like that, right? If I were to put it here, it would feel a force like that. Watch as I drag this positive test charge around and notice at any given moment, the force it's feeling is just aligned with the electric field vector at that location. If it were a negative test charge, it would be feeling a force in the opposite direction. Cool, right? And that's all the electric field is doing, showing us what the force acting on a positive 1 Coulomb charge would be if it were to be placed at that location in space. Okay, so here are some of those diagrams kind of showing what we were just looking at in the simulation, right? Again, though, typically we don't draw a million different arrows. We represent it this way, okay? With just these single arrows that are always pointed, the way that a positive test charge would be feeling a force, right? So here again, remember like we saw, right? It would be being pushed up and to the right by this positive, and it would be pulling down and to the right by this negative. So overall, up and right plus down and right gives us just to the right, right? A positive test charge at any of these locations would just feel pushed to the right. Okay, here in the middle, right? If there was a test charge right here, it would be feeling pushed up and to the right by this source charge, and up and to the left by this source charge. Well, up and right, up and left, the left and right cancel, giving us just up, and that's why the electric field there is up, okay? We'll look more later in this lesson at adding multiple electric fields from multiple source charges when they kind of overlap because there's more than one source charge, but just wanted to show you the images there. Okay, so note that the electric field, as we've been talking about, has a defined direction at each point in space, right? It is a field that has not just a magnitude, it's not just telling you how big the force a positive test charge would be, but also the direction that force would be. And so that doesn't come as a surprise. We kind of talked about this earlier in the lesson, right? Fields that are associated with a vector quantity, like a force, are known as vector fields. Just like our wind map that we started out this lesson talking about, right? That's showing you the velocity of the wind, how fast it's moving in what direction. No matter where you were here, This is a vector field because it's showing you what the force would be like, and force is a vector, like velocity. Now, usually with a vector, to show how large it is, we draw a bigger arrow, right? Like to show a stronger force or a faster velocity or a bigger momentum, we would draw a longer arrow. The problem with that here is that the electric field actually does extend out to infinity, right? I mean, even the equation shows us that. No matter how big we make R, no matter how far we are from this source, it's never going to be zero. Even if I make R 1,000,000,000, this is going to be a tiny number when I divide by a huge number, but it's still not going to be zero, right? So the problem with drawing a bigger arrow to represent a larger electric field is that it extends kind of forever, right? So the way that we show it, and that kind of naturally happens when you draw the diagrams anyway, which is nice, is that we show larger magnitude, a stronger electric field, by an increased density of the field lines. Okay, so like it says here, right, based on just the diagrams, if we only knew that stronger fields were represented by more dense field lines, where would we expect the field magnitude then to be larger or smaller, right? Well, I mean, we can see if we look here, right, closer to the charge, if I draw a little, let's just draw a little line to say, I can get 3 field lines into that line there. But then if I move out a bit and I draw the same size line, I can only fit 2 field lines onto it, right? And if I go out even further and draw the same size line, suddenly only 1 field line actually fits into it, right? So notice how they're getting less densely packed as we move further away from the source charge. What does that tell us about the strength of the electric field out here versus in here? It's getting weaker as we move further away from the source. Okay, so based purely on the diagrams, right, and what we know about the density of the field lines being used to visually represent, we can see that the field lines are always denser closer to the source charges, right? Now, it asks us, does this agree with what you'd expect based on your electric field equations? Well, what are our electric field equations? The main one for calculating what the electric field will be like around a given source charge is this, right? And so does our electric field equation suggest that as we get further away, so as R gets larger, should the electric field get weaker? Yeah, right? We'd be dividing by a bigger and bigger answer. In fact, this is a good old inverse square relationship. So yeah, I'd say so, right? If the electric field is equal to kq over r squared, then the electric field magnitude is inversely proportional to the square of r. So if r goes up, electric field goes down, right? The further we get, the weaker it gets, just like the lines on the diagram indicate by being less dense out here than they are in here. And finally, it asks, do both the diagram and the equation agree with what you'd expect based on the definition of the field, right? Well, the definition of the electric field is the force that a 1 coulomb positive charge would feel if placed at a given location, right? It's a description of what that would be like for the space, any given space where there might be charges around, right? And we know from Coulomb's law in chapter 10 that the force a charge would feel is inversely proportional to the distance it is away from another charge, right? So yes, I would say that checks out as well, right? We know that the force between two charged objects is kqq over r squared, right? So same idea. If r gets larger, the force between the two charged objects will get smaller, right? And so since electric field is just telling us about what the electric force on a positive 1 coulomb test charge would be like there, or there, or there, right? We would indeed expect that force to get weaker as we get further away, meaning the electric field is weaker out here, because that just tells us the force that a positive 1 coulomb test charge would feel if placed at any location. The further that location is from the source, the weaker that force will be, we know from Coulomb's law. All right, let's try out a couple examples thinking about the electric field, the electric force, and directions. So it says that a metal plate is given a positive charge. By the way, you're going to see a lot of reference to plates in this chapter. It's not talking about like a dinner plate that you would eat off. In electricity and circuits and stuff like that, we often use charged metal plates. It's just like a piece of metal essentially, okay? But it's given a positive charge at a point, and when they say point, they really do just mean a point, a place, a location, okay? So it's just a location, 2 centimeters above the plate. It asks us in A, is there an electric force? And if so, in what direction? So we've just got a positively charged plate, and we're interested in a point, right? Again, just a location. There's not anything there, according to this question anyway, that we can work out. So at a point, often the label for a point, we just use the letter P, a point P, and that point is 2 centimeters above the plate. Is there an electric force? So is there something here that's actually feeling pushed or pulled because of this positive plate? Well, no, right? This is literally just a location. We know that the electric field can let us think about what force a charge would feel if placed there. But if there's no object there, there's nothing for a force to actually be acting on, right? It's a bit like the Earth has a gravitational influence, sure. But if nothing is sitting here to actually feel a force, right? If this is just empty space, well, there's no force acting on it because there's nothing to pull, right? There's nothing to accelerate with a force. And this gets at the difference between a field and a force, right? Like I said, they're not the same thing. A field is sort of like a force waiting to happen, but it's not a force. We're saying there could be a force if an object were placed there. But based on the information we've been given here, we have to assume, like this point, we have no reason to believe there's any charge there at all. This is just a location. So is there an electric force? No. Right? There would need to be another charge there for this field to actually be exerting a force on, right? So, I mean, we even know that from the equation. How do we calculate electric force? We need 2 charges, and then we can calculate the force between them, right? But if there's no other charge here, there's not actually anything to exert the force on, right? Fields are almost like strength, like you have it all the time, but it's not until another object is there that you can actually exert something on it, right? You always have the potential to exert a force on something, but if there's nothing for you to exert it on, you're not actually exerting that force. Same idea with the field here. And so we kind of just touched on it, but in part B here it asks, is there an electric field at this location? And if so, in what direction? Okay, so it is near another charge, right? We know that charges generate electric fields. So this is generating an electric field, right? If another charge were to enter this field, it would feel a force as a result of that field, right? So this is generating a field. Remember, nothing needs to actually be feeling a force at the moment for the field to exist. Now, if so, in what direction? I kind of jumped the gun there and I drew it upwards. Do you see why we would call the electric field upwards or towards the top of the page? I'm going to start using that terminology more often, not things like up or down or left or right, but towards the top of the page or left of the page or right of the page or towards the bottom of the page, because directions are going to start to get, especially when we talk about magnetic fields, sometimes things will be even coming like towards us out of the page. So we like to be more specific in terms of what we mean when we say it. So I'll say the electric field, there is an electric field at the location P, right? This would be generating an electric field there, okay? And in what direction? Towards the top of the page. Now, why? Why that way and why not, down towards the bottom of the page? Well, remember, how do we define electric field direction? We ask ourselves, in what direction would a positive test charge feel if placed here? Right? Well, if placed here at the point P, right, a positive would feel repelled by this positive. So a positive test charge placed at the location P would feel a force upwards, away from this plate, towards the top of the page. Okay, so just kind of summarize what we were talking about there, right? Yes, there is an electric field, even if nothing's there to feel a force, right? Anything with charge generates, creates its own electric field. Okay, the direction would be away from this positive plate because again, right, we ask ourselves, in what direction would a positive charge feel a force if placed there? All right, now a similar example here says a sphere with excess electrons. Okay, so if it has excess electrons, we know that means it's negatively charged overall, right? It has more negative electrons than positive protons. Okay, now it accelerates towards a plate on its left. So it asks us first, is there an electric force on the sphere? Is an electric force acting on the sphere? And if so, in what direction? Okay, well, I mean, just thinking about that, it's accelerating. We know from physics 20 even, right, that, or even science 10, that a force is required to make an object accelerate, right? A net force can make an object accelerate. So definitely, yeah, there is a force acting on this sphere. So see the difference here? Now we do have another charge accelerating towards some charged plate, right? And the other charge is actually feeling a force as a result of being placed into an electric field, right? So just drawing a diagram here to get our bearings. I'm not going to say what type of charge is on the plate because that's what C is going to ask us, although you probably have a pretty good idea what type of charge must be on the plate if it's attracting a negative, if a negative charge is feeling a force towards the plate that's on its left, okay? But is there an electric force on the sphere? Yes, there is, to the left, right? That's why it's accelerating to the left. And really, all that's applying is Newton's second law, right? Physics principle number 1. The acceleration of an object will be equal to the net force acting on it divided by its mass, right? So if it's feeling a net force to the left, it will accelerate to the left, or vice versa. If it's accelerating to the left, it must be feeling a force to its left. Now, B asks us, is the sphere in an electric field? And if so, in what direction is the field? Well, it has to be in an electric field, right? An electric force can only arise from an electric field, right? That's kind of the whole idea of the electric field, is thinking about what could the force be like all around this charged object if another charged object were placed there, okay? So definitely, yes, I feel pretty comfortable saying yes. It must be in an electric field, otherwise why is it feeling an electric force? Now this part is interesting though. If so, in what direction is the field? Don't forget, how do we define the direction of the electric field? We define it as the direction in which a positive test charge would feel an electric force, right? So is this a positive charge that's feeling a force to the left? No, it's a negative charge. So if a negative charge is feeling a force to the left towards the plate, which direction would a positive charge feel a force if it were placed at the same spot? Right? Well, it would feel a force to the right, right? Obviously, if this plate is attractive to this negative charge, right, it's going to be repulsive to a positive charge, right? Electric field is defined as the direction a positive test charge would feel a force if placed there. But that means negative test charges actually feel forces in the opposite directions, right? No matter what, negative and positive test charges never feel the same force in the same direction, right? They're always going to feel forces in the opposite directions because what's attractive to a positive is repulsive to a negative, and what's repulsive to a positive is attractive to a negative, right? So yes, there is an electric field, but it is not towards the left like the force on the negative is, right? The electric field is always defined as how a positive test charge would feel a force. So if a negative test charge felt a force to the left, the electric field is actually to the right. Okay, and so then it asks us what type of charge is on the plate, right? Well, if it's attracting a negative, what must be the charge on this plate? It must be positive, right? Opposite charges attract. Now, let's back that up with what our electric field is doing, right? Notice our electric field is pointing away from the plate, right? Now, does that check out? Would this plate generate an electric field that points away from it? Well, yeah, right, because we think of electric field direction as the direction in which a positive test charge would feel a force. And a positive test charge would be repelled by this plate, so it would want to get away from it, right? So over here, the electric field generated by this plate would look like this. Of course, on the other side, the electric field generated by it would look like this. Up here, it would look like this. Obviously, we're not thinking about these parts of it for this question, but that's what the electric field surrounding a positively charged plate would look like. Because electric field direction, again, I can't stress this enough, is defined. It's by definition the direction in which a positive test charge would feel a force if placed there. Now here's an interesting one. If we replaced the test sphere, so this object that we've put into this electric field, if we replaced it with one that had a deficit of electrons, so we took this away and we switched it out for one that had a deficit of electrons, which means it's now got what type of charge? Positive. How would our answers to A and B change? Okay, so A asked us what the direction of the electric force on the sphere would be, right? Well, if I swapped out this negative for a positive sphere, right, how would the force acting on it change? Well, now it's going to feel repelled away from this positive plate, right? Or another way we can now look at this, now that we've discussed electric fields, it's going to feel a force in the same direction as the electric field that it's placed in, right? So for A, our answer would change to the right, away from the plate. Okay, so the force acting on our sphere would change if we swapped it out for a positive sphere instead of a negative one, right? Like repel, positive would repel a positive. And also positive charges feel a force, an electric force, in the same direction as the electric field they're placed into. But what about our answer for B? Would our answer to B change? Okay, we'd be placing it into the electric field. Now, what is the electric field? What's the source of this electric field? It's the plate, right? The plate is generating this electric field that is causing this electric force on our sphere. Does swapping out the negative for a positive change anything about our plate and its charge and its properties? No, right? This field, this electric field that we've drawn here, is created by this plate. It belongs to this plate, so to speak. It doesn't care what's over here, right? If we put a negative in, that negative will feel a force in the opposite direction as the electric field. If we put a positive in here, the positive charge will feel a force in the same direction as the electric field. But the electric field is still in the same direction. It's just that if I were to put a positive into it, well, now it would feel a force in the same direction, right? That's how electric field is defined in the first place. In which way would a positive test charge feel a force if placed into this field? So for B, our answer would not change. Okay, so again, right, nothing has changed about the source of the electric field we're talking about just because we put something else into the electric field. It's still a positive test charge, or sorry, source charge, right? Putting in a different test charge isn't going to change the electric field being generated by this source, right? I mean, think about it in terms of the gravitational field. Does the Earth's gravitational field change because you've put an apple at a certain location, or you've put an elephant at a certain location, or you've put a nothing at a certain location? No, right? The Earth's gravitational influence is still the same because you haven't changed the mass of the Earth or how far that location is from the Earth, right? You've just put something else there. But the Earth's gravitational field is the same there either way. Remember, part of the whole point of a field is we can even think about the field if there were nothing there at all, right? Think about the force a charge would feel if placed there. So putting something different there has no effect on the field itself. To change the electric field here, we would have to change something about what's generating the electric field. All right, so as we've mentioned, right, the electric field is a vector, right? I mean, we know it has a magnitude and a direction, okay? And like any other vector, it can add together, right? So when there's multiple charges, each producing their own electric field, like this would make an electric field if this one weren't here at all. This one would make an electric field if this one weren't here at all, right? So when those vectors are kind of overlapping with each other, so to speak, they just add to give the overall electric field at a given location, right? So again, like this one's electric field does just kind of look like this, right? It's a positive charge, so positive charges would feel forces away from it, kind of like this, right? And this one is doing the same thing. It's just that when those meet up, right? So when you have them next to each other, like this, let's say, right? And we were to ask ourselves, okay, well, what would the overall electric field be like, let's say, right there, right? We know this is generating an electric field at that location. This would also be generating an electric field at that location. So what's the kind of net electric field right there? Well, we would add them like any other vector, right? I mean, if I were here, I'd be feeling, if I were a positive, I would feel a force up and to the right. If I were here, I'd be feeling a force because of this one up and to the left. So we could draw a little electric field vector addition diagram, right? You'd be feeling from this one an electric field something like that, from the other one an electric field something like that, right? And so what's the net electric field like there? Well, it would be like that, right? That would be the net electric field. So it asks us if we can kind of see the connection between these two images, right? That is essentially what this one is showing us. It's saying, really, this image here is just the result of doing a little vector addition of the electric field from this one and this one at every location. So just take a look, right? And notice that the direction of the electric field here and here, it's just doing, like, for example, between the two charges, like the one we just did, right? Up here above between the two charges, right around here, look at the little VAD they've drawn. They've got an arrow that's up and to the left and an arrow that's up and to the right. Well, if this is a positive charge, it's going to generate an electric field at this location that would push you, if you were a positive, up and to the left, right? While this one would be pushing you up and to the right, because these are positive, they would repel a positive, right? And so if we add those two tip to tail, like we would any other vector, like we would displacements or forces or velocities in physics 20 or momenta in physics 30, right? If we add them tip to tail, the net electric field would just be up. Their x components cancel each other out, right? Sure enough, on the diagram, up, right? What about, like, right in the middle, for example, right in the middle, it's actually a very low density of field lines there, right? Implying a very weak field here. Well, that actually makes sense too, because a positive would repel from this one just as much as it would repel from this one if it's exactly at the midpoint. So it would feel a force to the right just as strong as the force to the left, and those two would add tip to tail to cancel each other out perfectly, right? So there is a point between these two charges where the electric fields actually cancel out, right? You can imagine finding the perfect spot to put a positive charge that it would feel no overall force. It's just as repelled by this to the right as it is by this to the left. So they cancel each other out, right? No matter where you look, you can see that, oh yeah, if I just add, over here, I'd be pushed very strongly down and to the right by this charge, and also down and to the right by this charge. So look, down and to the right, down and to the right. So the net electric field is down and to the right, right? Over here, how would you feel? Well, you'd still be repelled by this one, just not as strongly if you were positive, and repelled by this one to the right, but much more strongly because you're much closer to it, right? And look at the VAD they've drawn over there, right? A very strong electric field to the right, and then also to the right, but not as strong because we're further from charge A. It's the flip version of that over here. Very strong electric field to the left from positive charge A, and a slightly weaker one, but also to the left from charge B. Okay, so don't forget, vectors add, whether it's a displacement from your walk, right, a velocity from boats on a river like we did in Physics 20, or momenta like cars in a collision like we've done in Unit A of Physics 30. All vectors can be added and they all follow the same principles. So like I always say in physics, right, you're really going to learn like a couple skills and then you just apply them in a lot of different ways. So we're going to do 2D vector addition with electric fields, but it's not going to be applying any super different ideas than what you did with displacements. It's just that now the vector we're adding is an electric field. It's a quantity with a magnitude and direction, just like displacements were in Physics 20, and we add them following the same principles. Let's try this one out. And this is actually one from an old diploma as well. So let's take a look. As always, I kind of find with these, it's nice to read the question first before you read all the information, just so you kind of know what you're looking for. So the electric field will be 0 at the location labeled, okay, 1, 2, 3, or 4. So we got some locations, some charges. We want to find where the electric field will be 0. So 2 charges, positive Q, and then negative 16Q. So it's just saying if Q is the amount of charge, right, this has 16 times more charge than this, but it's negative while this is positive, okay? Each labeled location represented with a dot is equally spaced. Okay, so it's saying this is just as far from this is from this, as this is from this, etc. Okay, so what we want to know is where will the electric field be 0? Now, this is producing an electric field, right? It has charge, so it is producing its own electric field. This also has charge, so it's producing its own electric field. But where they meet up, they might vectorially add at certain locations to give us 0 net electric field, right? Just like here, right? Right in the middle of these two, yes, this is producing an electric field, and yes, this is producing an electric field, but they add in such a way to cancel each other out perfectly right at their midpoint. Now the difference here, we can't say it's actually going to be right at their midpoint, partially because that's not one of the options we have, right? We have to pick one of these locations, and the midpoint would be right here between 2 and 3. But the other reason we know it's not the midpoint anyway is that these aren't equally charged, right? And we know that the magnitude of the electric field is K times this charge of the thing that's producing this electric field divided by how far away you are from it squared, right? So this is going to naturally produce a stronger electric field than this. If we're the same distance from this one as we are from this one, then this is going to have a larger electric field at that location, right? It's got 16 times more charge. So let's just look here. Let's see if we can eliminate any right off the bat, okay? Let's think about it. If I were a positive charge, because that's what we always think about for defining and thinking about the electric field direction, okay? If I'm at position 1, I would feel, how would I feel about this charge? Repelled to the left or attracted to the right by this one? I'd feel repelled to the left, right? Because like repel, okay? And then how would I feel about this negative charge? Attracted to the right or repelled to the left? I would feel attracted to the right if I were a positive test charge here, right? Opposites attract, so I'd be attracted to that negative charge. Okay, so from one of our fields, or one of our source charges, I would feel repelled to the left, and the other I would feel attracted to the right. So I wouldn't say we can rule out one just yet then, right? We have two vectors in opposite directions. It's possible they could add to 0. So we're going to have to do a little more thinking about that one. We can't cross it off immediately. Let's look at position 2. If I'm at position 2 and I'm a positive charge, because that's what we need to think about for the electric field direction, okay, I would feel a force because of this one to the right, right? I'd be repelled to the right. And I would also feel attracted to the right by this one, right? So the electric field generated by this at location 2 will be to the right because that's the direction a positive test charge would feel a force because of this charge if it were placed there. And the electric field generated by charge B here would also be to the right because that's the direction a positive test charge would feel a force because of this one, right? So the electric field from this one is to the right here, and the electric field from this one is to the right here. We have two electric fields to the right. Can those add to 0? Can they cancel each other out? No, right? And it's the same story at position 3. Those are both going to be, it's going to be repelled to the right by this one if it's positive, and attracted to the right by this one if it's positive. So the electric field is in the same direction from charge A and from charge B at both positions 2 and 3. So there's no chance they could ever add to 0. So B and C don't make any sense, right? How could the electric field at positions 2 and 3 add to 0 if the two charges producing the electric fields and their electric fields at that location would both be to the right? Now, finally, moving on to position 4 here, let's see if it's at least a possibility based on what we've been talking about. If we were at position 4 and we were a positive test charge, we would feel attracted to the left by charge B, right? So the electric field generated by charge B here looks something like that, right? It is towards the negative because that's what a positive would do. So at position 4, the electric field from charge B would be to the left, okay? And what would the electric field that's generated by charge A look like here, right? Because again, remember, these electric fields, they extend out to infinity. Really, this is what the electric field looks like. Okay, but if you were a positive test charge placed at position 4, because of charge A, you would feel a force to the right? You would be repelled by this to the right. Okay, so we can't quite eliminate 4 until we do some more thinking, because the electric field generated by this one at position 4 and by this one at position 4 are at least in opposite directions. So it's possible they could cancel out. So we've narrowed it down to 2 choices. Okay. However, remember, we can't just say, oh, opposite directions will automatically cancel each other out. They have to be in opposite directions and be the same size, right? These 2 vectors, for example, they don't cancel each other out. They just give us a net field to the left in that case, right? Slightly smaller than it would be if this one hadn't been there, but still an overall field. They don't perfectly cancel each other out. We would need the net electric field to be 0, meaning that the 2 fields we're adding are the same size and in the opposite direction so that they perfectly cancel each other out. For that, we'll have to think about the equation that tells us about the electric field generated by a source charge. So let's first think about it at position 1. Okay, now at position 1, we are closer to the charge that has a smaller magnitude, right? This one has 1/16 as much charge as this one. So this distance from 1 to here, right, is it's 1, 2, 3, 4. It is 4 times further away from charge B than it is from charge A if we look at position 1. Ooh, okay. So 4 times the distance. 4 times the distance. What would that do to the electric field strength? Be careful. We're dividing by r squared, right? So if something is 4 times further away, but that distance gets squared, right? Notice we're not actually making the electric field 4 times weaker. We're making it 4 squared times weaker, right? We're dividing by 16, 4 squared. So hey, that actually works out, doesn't it? Because yes, this one is, this charge is 16 times larger. And that on its own would make the electric field 16 times stronger, right? If that were the only difference here, we would be multiplying the charge by 16, and charge is in the numerator of this equation, so that would make the electric field 16 times stronger, right? But that's not the only difference. It's also 4 times further away. So those 2 effects would cancel each other out. It has 16 times the charge, but it's also 4 times further away. So being 4 times further away would make the electric field 16 times weaker, but then the charge is 16 times stronger to make up for that, right? We're essentially multiplying by 16 and dividing by 16. So I actually think 1 is our correct answer, right? It would be, the electric field we know would be to the left from charge A, and it's much closer, but then it's to the right from charge B, and it is much further away, but it's also got 16 times bit larger charge magnitude. So the electric field should actually have the same magnitude from charge A at position 1 that as it does as charge B at position 1, but in opposite directions. So those would add to give us 0. And just to make extra sure, let's look over here at position 4, right? Well, this one's got it all backwards now for what we would need, because look, it's much closer to the stronger of the charges. So it's 1/4 the distance. We know that would make the electric field 16 times stronger, right? If the distance is 4 times smaller, the electric field from this would be 16 times larger from charge B than it would from charge A. Plus, charge B is also got 16 times more charge. So not only is the electric field 16 times stronger from just being 4 times closer to charge B than charge A, but it's another 16 times stronger because charge B has 16 times as much charge as charge A, right? So this would actually be 16 times 16, 16 squared times stronger electric field. So I won't even be able to draw it to scale. It's going to be so much larger. That would be the electric field at position 4 because of charge B, right? Very strong to the left, okay? Very big charge that's very close by. And then it'd be a lot weaker from charge A. There's no way those are canceling each other out perfectly, right? Not only does this have 1/16 the charge, so our charge would be 16 times weaker, it's also 4 times further away. So this electric field generated here is just way too weak compared to this thing's electric field being generated here for them to actually cancel each other out. And so definitely I think our correct answer then would be A, okay? At position 1, they would add to 0. Okay, let's try one here now where we actually think about the electric field in 2 dimensions. Okay. So it says that 2 objects, each with a charge of -6 nanocoulombs. Okay, so those look like our 2 charges. They're placed 4 millimeters apart, as shown below. Calculate the magnitude and direction of the electric field at the point P. So again, this is just a location, right? This generates an electric field there. This generates an electric field. If we were to put something there, it would feel a force because of the combined effects of these 2 charges' electric fields at that location. And the point P is 12 millimeters directly above the midpoint between the 2 charges. All right, so this is kind of nice actually because they have the same charge magnitude, right? They're both having charges of -6 nanocoulombs. And this point is at the midpoint above them. So the nice thing about this is that, okay, they're both negative, and the electric field, and they're both the same distance because of this midpoint fact, right? Which means the electric field actually in one axis, you can kind of predict here, and we'll draw a vector addition diagram of VAD in a second to confirm, but in one of the axes, it might actually cancel itself out and save us some calculation. Not that we couldn't deal with it, right? What we want to do is calculate the net electric field. Well, we know that the net electric field from this is going to have an X and Y component at the location P, and the net electric field from this is going to have an X and Y component at the location P, right? If we add up all the X components, we'll have found the X component of the net electric field at P. If we add up all the Y components, we'll have found the net Y component of the electric field at P. So we're still doing the same thing we did back in Physics 20, right? We're going to find the net electric field in the x-axis by adding up the X components of every electric field generated by every charge at whatever location we're looking. Now, obviously, this isn't specific to this one we're dealing with, but this is the same general idea, right? Then we find the net Y component of the electric field at a given location by adding up the Y components of every electric field that is at that location, right, from each object. And then once we've got those two, we can use Pythagorean theorem to find the net electric field itself. And finally, some trigonometry to get its direction, right? Sound familiar? It should. I mean, it's the same thing over and over, isn't it, right? They're vectors. They all work the same. It's just different quantities. In this case, it's the electric field that we're adding in 2 dimensions. It's just a different thing, but it's still a vector. It has X and Y components, and we can add those X and Y components, okay? So let's apply that process here now. So we're trying to find the net electric field at the point P, okay? This is producing an electric field in all directions. How is the electric field around this pointed? It's a negative charge, right? So what would a positive do? I'm just going to draw it everywhere. We'll definitely get rid of this because it would be too crowded, right? But the electric field surrounding this negative object that it produces would look like that, right? For this one, it would look like this because positives would feel forces towards it because it's negative. And the electric field direction is defined as the direction in which a positive test charge would feel a force if placed at that location. Okay, but we're not trying to think about everywhere right now. We're just trying to think about what is the electric field like at the point P, right? This is producing an electric field there. This is there. What do they combine to tell us the net electric field at the point P? Well, if you're at P, how do you feel about this charge? If you're positive, you would feel attracted towards it, right? At P, this is what the electric field generated by charge 1 at the location P would look like, right? And similarly, if you were at the point P, the electric field that's being generated by charge 2 at the point P would look something like that, right? Okay, so if we're at P, we're kind of in both of those electric fields at the same time, so they add together, as we would always do for a two-dimensional vector addition problem. Let's draw a vector addition diagram just to help us get our bearings a bit here. So I'll draw the electric field. Doesn't matter the order we draw them, we know that. I'll draw the electric field from charge 1 at the point P, and then tip to tail, I'm going to draw the electric field from charge 2 at the point P, right? And then we can see, all right, so our net electric field at P is going to look something like that, right? Which actually makes a lot of sense when we think about it. It's at the vertical midpoint, okay? So it's midway, well, sorry, the horizontal midpoint, right? It's in the middle of them. So as hard as this would be pulled to the left if a positive were placed here, it's going to be pulled to the right by this one if placed here. So it kind of checks out that the x components of these electric fields seem to be canceling each other out, leaving us with all y components. Let me just add to this diagram a bit. Okay, so I'll definitely get rid of this in a sec just because it does make the diagram overcrowded, but I want to do it to illustrate what's going on here, right? Again, the electric field from charge 1 at the point P, it's got a downy component, right? It's y component, and a lefty component, it's x component. We can do the same here now for the electric field generated by charge 2 at the point P, right? That would be E2's y component, and then its x component. It's downy and righty, right? So its x component is righty and its y component is downy, like this. And this kind of gets at an idea here that we can see, right? The electric field from object 1, its x component is just going to cancel with electric field from object 2's x component, right? Now, we can only be so sure of this because of the facts here, because of the fact that this is directly in the middle of them horizontally, and they have the same charge magnitude. They wouldn't cancel out if this had a bigger charge magnitude, because then this electric field would be bigger, right? And therefore its x component would be bigger and its y component would be bigger. So that would no longer cancel out with this one's x component, right? But in this situation, since they have the same charge magnitude and they're exactly positioned in the middle of them, we can actually be pretty confident with that. So we'll apply that. We can take advantage of that later when we're actually calculating. Okay, so like I said, I'm going to take those components out of the diagram just because it makes it a little too crowded, but don't be scared of writing sentences too, right? Like you can explain yourself with words. It doesn't all have to be calculations, but we could say that the net electric field in the x-axis is going to be 0 newtons per coulomb here because of the geometry of the situation, right? Because of the like symmetry here, right? The horizontal symmetry. They're the same charges and it's the same horizontal distance separating them, I should say, separating them and the point P. So what does that mean for our net electric field? Well, it's just actually going to be the result of adding the y components, right? It's just going to be whatever we get when we add electric field 1's y component to electric 2's field 2's y component, right? I mean, you can even see that. This net electric field is just the same as this plus this, right? This is the same as this. So our net electric field is just all y component, right? It's the electric field in the y-axis added up for each electric field. So in other words, It is. What is E net y? Same as F net y, or, displacement net y. Add up the y components of all the individual vectors. So electric field 1y plus electric field 2y. Now, how do we calculate the electric field for charge 1 here? Well, we've got a field for an equation for that, right? We know the charge that's generating the field, okay? And we might not directly have it, but I see a way we could figure out how far apart they are, right? This is just going to be the electric field from charge 1 there will be K times Q1 over R squared, right? Our electric field equation for when we know the charge of the thing creating the field and how far away we are from it. But in order to do that, we're going to have to deal with that problem. How far away from it are we actually? Now be careful here. A common student mistake with these is to say it's 12 millimeters away from charge 1, right? The location P is 12 millimeters from charge 1, but it's not, right? It's this far away from charge 1. So let's just draw a quick picture here to think about this. Because we need to know this distance, right? And of course this distance as well to get the electric field from charge 1 and charge 2. Okay, so I've just drawn the similar situation down here so we can kind of look at the geometry here, okay? I'm calling this distance R1P because it's the distance between our point P and charge that we've given the name charge 1, okay? So if we take a look, okay, do you see any geometry we can take advantage of here to figure out what this distance is? We know that this is 4 millimeters. From 1 to 2 is 4 millimeters, right? Now, we can't quite do any of our trigonometry like our Pythagorean theorem, for example, with this triangle here, because we know that that only works with right angle triangles. But hang on a sec, we actually kind of have 2 right angle triangles there, don't we? And this is the midpoint, it told us. So if the total distance is 4 millimeters, then this is 2 millimeters, and this is 2 millimeters. And what's more, since this is the vertical midpoint, right? Well, that tells us that whatever this is, it's the same length as this. So if we can just find R1P, we automatically know R2P as well. And if you take a look here, well, now we know, okay, this is 12 millimeters. This is 2 millimeters. Whoops, that wasn't very straight. And this is the distance between charge 2 and our point P. So we can use Pythagorean theorem to figure out what that is, right? It will just be that this squared equals this squared plus this squared, right? So I've written it out there. That means that R2P will be the square root of that. So squaring 12, squaring 4, adding them, and then square rooting, I got that the distance between them will be 12.165525 millimeters. Now we got to be careful. Do we like millimeters? No, right? And we know it won't work. Our Coulomb's constant, K, is set up to work with Newton meters squared per Coulomb squared, not Newton millimeters. So we're going to have to convert that to meters, right? But from the back of your formula sheet, millimeter means times 10 to the negative 3 meters, right? Or divide by 1,000. So 0.012165525 meters. And there we go. And like we said, right, because of the way the question was set up for us, this is the same distance. So now we have the distance between charge 1 and our location P that we're interested in the electric field at, and charge 2 and that location. Okay, so we are definitely on our way. We just need to figure out, okay, what is the electric field that would be generated here using KQ over R squared? And as we said, then we just need to find their Y components using some trigonometry and add them up. So let's just go ahead and as our first step here, let's just find what that electric field would actually be. Okay, now again, this is a 2-for-1, right? The charges are the same, their separation distance is the same, so their electric field strength is going to have to be the same too, right? Now, different directions, but same magnitude, which is all we're calculating right now, okay? So that will just be KQ over R squared. And we just found R, so we're good to put our numbers in. So K, Coulomb's constant, times the charge of our thing that's generating this electric field divided by how far away it is from the location we're interested in, squared, right? So that's what I've got there. And when I put that in my calculator, I got that it was 364,459.1635 newtons per coulomb. Okay, so remember what we said, right? What we've now got is how large this is. But because of our looking at the situation and feeling it out, we realize that actually the x components just cancel each other out, and it's only the y components that are adding up, and those y components actually give us the net electric field, right? The x's end up canceling each other out. So now we just need to figure out what is the y component if this is 364,459 newtons per coulomb. Okay, so now how would we find those y components that we need to find the net electric field, right? Like we saw here. Well, I mean, how do we find the y components of any vector? We use trigonometry and we need an angle, right? So if we have, which we do, we just found, if we have the electric field from either of these, right, we would normally say, okay, we could do some SOHCAHTOA with this to figure out its y component. Problem is, we don't have an angle here, right? But can we use this once again, right, to figure out what that angle there would be? Do you see how, right? This is the vertical line, okay? This is the direction that electric field from object 1 would be pointed, and it's just pointed along this line here, okay? So it's the geometry of the electric field situation matches the geometry of this situation, right? It has to. This is just a vertical line. It's straight up and down. This we know is directed straight towards charge 1, so that angle there has to be the same as this angle here, okay? So, can we use trigonometry, SOHCAHTOA, to find this angle here? I think we can, right? We have opposite, we have adjacent, we even have hypotenuse, but we calculated that. We might as well just use the ones the question gave us, right? So opposite, adjacent, how about tan? So the tan of theta will equal opposite, 2 millimeters, over adjacent, 12 millimeters. And therefore theta is just the arctan, or inverse tan, of 2 over 12, which gives me 9.5 degrees, right? Okay, so again, that's this angle here, right? I mean, look, the y component is straight down. This 12 millimeter measurement is straight down. The electric field is directed along the, measurement that goes from the point P to charge 1, just like this distance from the point P to charge 1 would be. So that angle has to be the same. So this is also 9.5 degrees. And therefore, if we're looking for the y component, which is what we need to add up to get the electric field net's y component, but since the electric field net is only in the y-axis, that would actually give us the full E net, okay? So we can see here that would be adjacent to the 9.5 degree angle. We have the hypotenuse. We calculated that in the previous step. So adjacent hypotenuse, that sounds like a job for cosine. So the cos of 9.5 equals electric field from 1's y component over the electric field from 1 itself. And therefore its y component is just going to be its electric field times the cosine of 9.5 degrees. Okay, and we've got the electric field magnitude. Okay, we calculated that in the previous step. So the electric field from object 1's y component, which again is the same as the electric field from object 2's y component, right? The geometry here is all identical. So that's going to be 364,459.1635 newtons per coulomb times the cosine of 9.5 degrees, and that gave me 359,460.8235 newtons per coulomb. So now, okay, what do we know? Looking back to our diagram, right? Our diagram can keep helping us. We know this is what we just found, and this has to be the same, so the net electric field is just going to be the result of adding that to that, right? X, again, cancels out. So E net X is just 0, and we therefore don't need to think about it when finding E net. So here we go. We can now go ahead and find the electric field, the net electric field at that location P, because of the interaction of the electric field from this and this at the location P. So we just got to add those up. Now, since they're both downward, I might go ahead and define downward as the positive direction. Why bring extra negatives into my math? So that just means the net electric field is going to be, we could multiply it by 2, or we could just say we've got two vectors pointed downwards that are each this strong, right? And just add them up like that. So when I did that, I got that the net electric field would have a magnitude of 718,921.6506 newtons per coulomb. Okay, so we just found it. The net electric field, the result of adding charge 1's electric field at P to charge 2's electric field at P. Now all we're missing, because electric field is a vector, is a direction, right? Now often with these 2D ones, we'd have to get an angle to get the direction, and we can still use an angle, but it's pretty quick in this case because it's just straight down, right? Straight towards the bottom of the page. So that angle is pretty easy to think about. We could just say it's 270 degrees, right? If this is 0, 90, 180, 270. So we get, how many sig digs do we get here? Ooh, we actually only get 1 sig dig because of the 4 millimeters there. Okay, well, that's all right. So our net electric field then would be 7 times 10 to the power of 1, 2, 3, 4, 5. 7 times 10 to the power of 5 newtons per coulomb. And the direction would be 270 degrees. Or you could say towards bottom of page. That would work as well. And there we go. Okay, so again, folks, it is the same. What's like the new stuff here for Physics 30? It was actually just this step. That was the Physics 30 step, calculating the electric field with KQ over R squared. Other than that, it was the same old 2D vector addition stuff, right? We've got a vector. It's got X and Y components potentially. We've got to add up the X components. In this case, that part was easy because we could tell the X components would cancel each other out. But then we add up the Y components, and we use those to figure out what the net electric field itself would be. Often we would need Pythagorean for that, but because the X component ended up being 0, we were safe to just add them up. It was all in the Y-axis. Okay? All right. So go ahead and try this one out. This is not necessarily a two-dimensional one because you can see here everything is lying in one axis. It's all in the x-axis, okay? But it's still good practice with adding up the net electric field. So it's asking you to calculate the net electric field at a point that is 2.1 times 10 to the negative 2 meters to the left of the 1.5 times 10 to the negative 6 coulomb charge, right? So at a point somewhere over here, it wants you to calculate what is the net electric field. Now again, this is going to be generating an electric field there. You can calculate that with KQ over R squared, right? And then this is going to be generating an electric field over there. You can calculate that electric field with KQ over R squared. You've got everything you need, right? And then all that's left to do is add those two electric fields, being careful about directions, opposite signs for opposite directions, same signs for same directions, all that stuff. Okay, and then at this point now you really can pause and try a few more practice questions out. At the very least, try this one while it's fresh in your brain. But I would also recommend taking a little break from my voice and, doing some of your practice assignment anyway, getting it done now, okay? These are some recommended practice ones from your assignment as well. This one's especially good for the 2D stuff, okay? So go ahead, take a break from listening and try it out on your own. Like I always say, physics is like riding a bike. You can't just watch someone else do it. You got to try it yourself to really understand it. And I should mention as well, okay, as always, folks, my solutions and the textbook solutions are posted for all the practice questions. So if you're getting stuck with them, of course, you can reach out to me and book a meeting, but you can also look to those for maybe some guidance or a push in the right direction. All right, we'll talk about charge distribution on conductors and then do some graphical analysis, and that will wrap up this lesson. All right, so remember that in a conductor, right, what makes it a conductor is that electrons are relatively free to move through them, right? And so if we have built up charge, if we have electric charge built up on a conductor, well, remember, a bunch of electrons, they don't like each other. So if there's excess electrons, they're going to want to get away from each other. If they're free to do that, they will. They'll spread out, right? they will push each other away to find the best distribution along the surface of an object, right? Like charges repel. So if you have a bunch of extra electrons on a sphere, for example, they're going to spread out to the edges of the sphere, right? I mean, imagine you're in a room full of people you can't stand being around. Where are you going to go to get away from each other? You're going to go to the walls, right? Move to the walls, get away from each other. Spread out as much as you can. Okay, so the excess charge on a hollow conducting object will therefore be distributed along its outer surface. Now, the shape of the object determines what this distribution, and therefore the surrounding field, ultimately looks like. So below, the charge distribution for different negatively charged conducting shapes is shown. It wants us to draw in the electric field surrounding each object. Okay, so if you have, like a flat conducting plate like this, and there's built up excess electrons on it, they're going to want to spread out. They're going to go to the outer edges, right? If you're in a room full of people you can't stand being around, and they can't stand being around each other either, they're going to go to the edges, right? Go to the walls to get away from each other, okay? So that's what we see here, right? Spread out along the edges, okay? So it asks for us to draw the electric field surrounding the object. Well, these are negatives in this case. Of course, it would look different if it had built up a positive charge, right? But the electric field is always defined as the direction a positive test charge would feel a force. So a positive test charge would feel a force towards this negative charge, right? Or towards this, like this. Right? Similar idea for this one. The electric field at a point there would look like that. At a point here, like that. Like that. Now for this one, we get something kind of interesting happening because it's not like a uniform shape. It's got bits that are a little more pointy than others. So the electrons are still going to spread out away from each other as much as they can. But in the corners here, you notice they kind of get a little more bunched up than usual, right? Like here, there's 3 electrons, but in the same size circle over here, I get 1 electron and a little piece of another one, right? So what ends up happening then is if we look, right, electric field there, you can see that the electric field ends up being a little stronger near those pointy bits, right? Because extra charge kind of gathers there. It's the same idea. If you're in a room full of people that can't stand being around each other, but there's these weird little corners and you all spread out to the walls, the people at the corners, whether they want to or not, they end up kind of closer to each other, right? Like these 2 people are closer to each other than these 2 people. They both tried to spread out, but because of the corners, they end up a little more bunched up. Just to give a little visual here, right? There are the electrons spreading out, but notice here at the corners, there's more electrons packed into a tighter space than, say, here, right? They have a little more room there, okay? A bar, same idea. A circle, they spread out. Triangle, right? Look at the corners. We get more packed in at the corners than we do at the edges. So that's what it's talking about here, right? If there are points on the object with higher curvature, in other words, like pointier than other places, the charge will accumulate more there, and therefore the electric field will be stronger around these points. This is actually the idea behind like lightning rods on the tops of buildings. Have you ever seen a building like this? Like a tall skyscraper with a kind of a point on the top of it. The purpose of that is actually, believe it or not, you want them to get struck by lightning. The reason is these can handle it. They're engineered. They have conducting things that bring that charge down to the ground. So they can easily accept that charge, and built into the walls is conducting material that takes it and safely just transfers it to the earth, or from the earth to the lightning cloud, okay? And the other reason is it's actually good to take a little bit of lightning strike, because what that prevents then, you don't want so much charge built up that you get a huge lightning strike, right? It's good. It essentially takes off some of the charge so that you get smaller lightning strikes that aren't too damaging, and it doesn't build up into a huge lightning strike. So if we think about that lightning rod there, it's actually just taking advantage of this fact, right? If we imagine that, it's a lightning storm and some charge has built up, we want it to build up at the top here more than lower places so that it can more easily, right? Here the electric field is very strong, and there's strong forces on those electrons allowing them to be pulled out. That's why it's pointy like that. Now, an interesting fact about these hollow charged conductors is that at any point inside of them, the net electric field always adds vectorially to 0, which is interesting. So believe it or not, even though this is a charged conductor, right? This is full of extra charge. It's got a net charge. Anywhere inside of it, there's actually no electric field. Now, how can that be possible? Well, okay, let's imagine you're right in the middle, okay? And you were a positive charge. You would feel a force that way, so there's an electric field that way, right? And one that way, and one that way, right? All the way around like that. Do you see how all of those electric fields, though, would add up to 0? Right here, let me draw the VAD if you don't believe me. I'm going to add all of those electric fields for all the many excess charges on the outer surface, thinking about what field they would be producing inside the hollow conductor. Here we go. Let's add them up tip to tail. So we've got one that's up. Then we've got one that's up and to the right. Then we've got that's just to the right. Then one that's down and right? All the way around, just adding these up tip to tail. And look, I get right back to where I started, which means there is no net electric field, right? They've all added up to cancel each other out perfectly. Now, often at this point, students will say to me, okay, yeah, sure, if you're right in the middle, I guess they all cancel each other out. But what if you're up here? Surely they couldn't cancel each other out then, because then you're closer to these ones and the electric field would be stronger. But don't forget, that means there's now more charge below you. So yes, it's true, the electric field generated by this one here would be stronger because you are closer to it. And E equals KQ over R squared, right? So smaller R results in larger electric field. But there's now more charge below you. So the Q part of KQ over R squared below you is larger. Essentially what we're dealing with is this. Right? Not the world's best drawing, obviously, but the upward electric field parts are larger, sure, but there's less of them because there's less charge above you if you move up. And that works out no matter where you put it. If you go to the right side, the electric field from these will be stronger, but there will also be less charge to your right and more charge to your left. And so that effect works anywhere inside a hollow charged conductor. The net electric field is always 0. And so these hollow conductors, we often call them Faraday cages. There's a little more, like a Faraday cage is often also associated with protecting you from external electric fields. I'll show you how that works in a sec, okay? But this is the general idea, is that anywhere inside, right, anywhere inside the cage, the field adds to 0. And so we call these Faraday cages, they're used to like protect electronics and stuff if they might be exposed to electric fields. Because even if there's a lot of electric field stuff going on outside, like there would be here, right? There definitely would be a lot of electric field out here. Inside, those all add like that to cancel each other out. So here's just a little animation showing how a Faraday cage can protect from even electric fields that have nothing to do with it outside, okay? So what you'll see here is an external electric field applied. There it is. That makes all the electrons move to one side, though, which makes that side extra negative, and then the electric field is in the opposite direction, right? So there's an electric field here applied to the right, so the negatives all move to the left, but then that makes the right side more positive, so it creates another electric field there to the left that cancels out with the external one that was to the right. It's just vector addition of electric field, making the inner part have a net electric field of 0, right? So again, one more time, electric field to the right, so all the negatives move to the left, but that creates another electric field now to the left, which cancels out with the external original electric field that was to the right. All right, and so the last thing we're going to talk about here is graphing this electric field equation, okay, these relationships, and how to analyze those graphs, of course. That goes hand in hand with graphing anything, right? We often want to actually analyze those graphs to get information out of them. So it tells us that students measure the electric field around a Van de Graaff generator at various distances. Again, a Van de Graaff generator is just a way to build up a lot of charge. It's one of those big like silver balls you might have touched at like the Tellus World of Science or something, makes your hair stand up, okay? But it wants us to determine the magnitude of charge on the generator using graphical analysis. And they've given us the students' data here. So they did it at various distances, right? So they measured it at various distances, and this was the resulting electric field. So when they were 10 centimeters away from the generator, it was 90 millinewtons per coulomb. 20 centimeters away, 23 millinewtons per coulomb. Okay, so that's their data there. Now, let's just think about this first, right? Whenever we're sketching a graph, we kind of got to decide what goes on our x-axis, what goes on our y-axis. Now on the x-axis should always be the manipulated or the independent variable, right? The thing that we changed, okay? Well, what did we change here? They measured it at various distances. So they varied the distance, right? I mean, think about doing this experiment. You're in control of where you measure. That's what you can change about the situation. And in response to that, as a result of measuring at different distances, you will find that the electric field is different. So the electric field depends on what distance you're measuring it at, right? This is our responding or dependent variable. This is our manipulated or independent variable. Now we know when we're graphing, we should always put the responding or something to do with the responding variable anyway on our y-axis, and we should always put the manipulated or something to do with the manipulated on the x-axis, right? But the problem here is if we make a graph that is just this, will we be able to do graphical analysis with it, right? Because what equation governs this relationship? Well, we know that it's the electric field is going to be KQ divided by R squared. So what's the relationship between the electric field and the separation distance? Well, it's inversely proportional to the square of the separation distance, right? Now, what do we need to be able to do graphical analysis? We need a straight line, right? Is this graph then going to give us a straight line? No, it's going to give us the inverse square graph, right? It's going to give us this. We will not be able to do graphical analysis with that. What's the slope of this line? It has many different slopes. We can't say that, right? What's the area underneath this graph? We don't have any formula for the area of this shape. Until we learn integral calculus, we can't find the area under this, right? Intercept, no, not going to work very well. And graphical analysis is always about finding a slope, an area, an intercept, sometimes reading values off the graph, right? Pretty much all of those to work well require a straight line. But hey, in chapter 10, we learned how to straighten graphs. So remember, when we say this, yes, we are saying that the electric field is inversely proportional to the square of R. But at the same time, we're saying, look what we're saying. We're saying the electric field would be directly proportional and linearly proportional to 1 over R squared. So remember, right, when you want to straighten the graph, start by asking yourself, okay, what's actually the relationship between what I want, what my responding variable is and the manipulated? And in writing out that relationship, you can kind of see how you can almost, it feels like cheating, doesn't it? We're going to just kind of bend the rules a bit here and say, okay, so instead of making this graph here that would give me this shape, that's no good for graphical analysis because I can't do slope, area, or intercept, let's instead make this graph here. Not electric field as a function of R, but electric field as a function of 1 over R squared, the inverse of the separation distance squared. And look, right, if I double 1 over R squared, I double the electric field. If I triple 1 over R squared, I triple the electric field. If I cut it in half, I cut this in half. Well, that's a linear relationship. However, 1 over R squared changes, right? Whoops. The electric field changes by the same factor, right? So yes, changing R is going to change the electric field in the opposite way and squared, right? Doubling R is going to divide the electric field by 4. But doubling 1 over r squared is just going to double the electric field. So this would give us a straight line, which then we can do graphical analysis with all day, right? We could find a slope, an area, an intercept, whatever we wanted, okay? So with that in mind, I mean, we know we're eventually going to have to use this to find the magnitude of the charge. We will, as always, let the equation tell us how to do that, whether we want slope, area, or intercept. But before we do any of that, we're going to need a graph with a straight line. So in order to do that, we figured out that we need to make this graph, right, and not this graph. But to do that, we need to figure out all of our 1 over r squareds, right? These are no longer going to be our x values. Our x values are going to be 1 over r squared. So that's why they've left us this blank column here, okay? So these are our r's, right? We really are just going to take the r's, how far we are from the source of the charge. We're going to do 1 over it squared. Just be careful. Always check your units carefully. These are centimeters, right? So we'd have to divide by 100 to get meters. Okay, but if r is 0.1 meters, then the corresponding 1 over r squared is just 1 over 0.1 squared, right? Which gives us 100, right? 0.1 squared is 1/100th. 1 over that, 1 over 1/100th is 100, right? This one, 1 over 0.2 squared, which gives us 25. Okay, and there we go. These are now going to be our x variables. We can tell this worked a little bit better now, right? Because look, before, when r was, for example, doubling, the electric field was getting roughly 1/4, I mean a little bit less than that, but 1/4-ish as large. But then when r tripled, it got 9 times smaller, right? When r went from 10 to 30, the electric field went from 90 to 10. This is not a linear relationship, right? Doubling it made it about 1/4 as large, but then tripling it made it about 1/9 as large. Quadrupling it made it about, well, 1/16th-ish as large, okay? So r is not linearly related to the electric field strength. But 1 over r squared, look at this, 190, okay? When 100 became 25, well, that's about 1/4 as large, right? And this became about 1/4 as large. 100 to 11, 90 to 10, that's pretty close to linear, right? 100 to 6.25, 90 to 5.6. You can see how these are closer to a linear relationship than these two would be, right? One thing we are missing here is our units for 1 over r squared. Remember, r is measured in meters. These are 1 over meters squared, right? So 1 over meters would be meters to the -1. 1 over meters squared would be meters to the -2. Okay, so let's make our graph now then. Remember, the titles, we don't need to be creative. It's always just y as a function of x, responding as a function of manipulated here. Okay, so our y variable we said would be electric field, and our x we said would be the reciprocal of the distance squared, right? 1 over r squared. So then on our y-axis, let's put in our electric field. And can't forget our units. I might actually stick with the millinewtons per coulomb. I'll just have to remember that later when I'm doing the math, that these represent millinewtons. So we'll have to convert them when I go to actually do the calculations. But for making the graph, I kind of like these numbers. It's roughly 0 to 100. So it'll be kind of nice to work with. Okay. Then on our x-axis, we've got the reciprocal of the distance squared. And as we said, that would have units of inverse square meters, right? Meters to the -2. Okay, now we just got to set up our labeling and our scaling. Always take a look to see, okay, what's the like how high do we have to go, right? So that we can plan out our graph well. Like I said, electric field, it's about 0 to 100, give or take. Obviously, it's not exactly 0 to 100, but I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 squares. So if I make So maybe I'll make every 4 squares be like 25. I realize that's not the best. It's kind of annoying that we've got, like a quarter of 25 and then half of 25, but it's not the worst thing on earth, right? 6.25, 12.5, etc. to 25. I think that'll work pretty nicely. It'll spread out my graph fairly well. So I'll go 25, 50, 1, 2, 3, 4, 75, 1, 2, 3, 4, 100. And then on the x-axis, it's actually basically the same thing, right? Again, basically 0 to 100. I also have 18 squares here. Oh, actually, no, I don't. I have 20. I have 2 extra. So I can actually, I'll make every one represent 5, because 5 times 20 will give me 100. So I'll just make every square represent 5. So I'll go up by 10s, so 10, 20, 30, all the way up to 100 like that. Okay, and I just went in and added my halfway points between the major ticks on the y-axis there. Okay, and then of course we've got 0 and 0. So now we just got to plot our data points. So remember, these are now our x values. So when x is 100, y is 90. So let me add that point onto the graph. When our reciprocal of the distance squared is 100, the electric field is 90. So roughly there, right? 100 on the x-axis and a little above the 87.5, okay? Halfway between these two would be 93.75, I think, right? So that seems reasonable, a little closer to the 87.5. And now I'm just going to keep adding my other points in. So I'll do when x is 25, y is 23. So when x is 25, y is 23, okay? Let me add in the other ones. We've just got to add in the point now when x is 11.1, y is 10, and when x is 6.25, y is 5.6. So let's put those on our graph. So those would go around there, right? 11.1 and 10, and then 5.6 and 6.25. Feel pretty good about that. Okay, or sorry, 6.25 and 5. Feel pretty good about that. Looks like, hey, look, it gave us a pretty linear relationship. So before we move on, okay, before we actually start thinking about calculating here, let's just draw our line of best fit, because we know, again, if we did all of these experiment points and we just used 2 of them to find the slope, then what was the point of doing all the other trials of the experiment, right? We want to now get a trend line that shows us the trend in the data, the line of best fit. So I'm going to pull out my ruler, okay, I'm going to do my best to, again, more than anything, make sure it represents the trend in the data. So step back and visualize the line that would represent this data. And then, right, draw it through, trying to keep about as many points above as below and not forcing it through any points. So that's how mine came out. These ones were pretty good. The data was pretty linear. So I actually was able to get every point on the line. Always nice when that happens. Means these students did a really good job on their experiment. Their data seems pretty reliable. It all fits the trend very well. There's no outliers, okay? Or I guess they could all be wrong, but all wrong in the same way, which is pretty rare to happen. Okay, now, what are we going to do with this graph? We are trying to figure out the magnitude of the charge on the generator using graphical analysis. So like always, it's not a guessing game, right? It's not saying, oh, I don't know, I'll see if it's the slope or maybe it's the area, right? Let the equation tell you. So what equation relates electric field to the separation distance, or the reciprocal of the separation distance squared, right? Let this tell you what equation to be thinking about. And also to charge, because that's what we're trying to figure out, right? So what equation relates charge, electric field, and the separation distance squared? Well, if you go to your formula sheet, right, I can only think of one. It's this one, right? The electric field equals K times Q. Q is what we want to find over R squared. Okay, now this is on our y-axis, right? Now, r squared isn't our x-axis, but 1 over r squared is. Maybe if I rewrite it, we can see it a little more clearly, right? Do you see how those are the same? And now, there's our y variable, right? There is our x variable. So we're knocking at the door now of figuring out, okay, how do we actually use this graph to find what we want, which is Q, the charge, right? Well, I'll show you 2 ways, but look here. We've got a line. Notice how this looks a lot like the equation of a line. We've got y equals stuff times x, right? And remember, the equation of a line is y equals mx plus b, right? Where m is our slope and b is the y-intercept. So this is y equals mx, and our b, our y-intercept, would just be 0, which, hey, that even kind of matches with our graph, right? Our graph's trend did suggest that the y-intercept would be at roughly 0. So what does that mean for KQ? What is that? We have y, our y variable, equal to this times our x variable. Well, this must be m then, right? That's our slope. So hang on a sec. The slope is just k, which we know, that's Coulomb's constant. We always have that. It's a constant, right? Times q, and we're looking for q. So q would just be the slope divided by k. So if we can find the slope of this graph and then divide it by Coulomb's constant, 8.99 times 10 to the power of 9, right? We should be finding the charge on the Van de Graaff generator. Now, if you don't want to do it that way, if you want to do, the way of saying, I like just solving for q and then seeing what I'm doing with y and x, that'll work as well. So if we have that the electric field is equal to kq over r squared, and we say, okay, can we just isolate for q and see what we're doing with y and x and do it that way? We can, right? Multiply both sides by r squared and then divide both sides by k. And we're close there. This is our y, but this isn't quite our x, right? But notice e times r squared, that is actually the same thing as, right, e divided by 1 over r squared, because dividing by a fraction is the same as multiplying by its reciprocal, right? So e over 1 over r squared is the same thing as e times r squared over 1, or e times r squared. So this actually is our y variable being divided by our x variable. And then that's all being divided by k. So the charge is equal to, look at this, y over x, and then that's being divided by k. So it's rise over run, right? Rise over run. Change in y is a rise. A change in x is a run over k. And look at that. We got the same result, right? We got that q will be found by getting the slope of our best fit line and dividing it by Coulomb's constant, 8.99 times 10 to the 9. So we're basically done. Now we just got to go back to Math 10C and actually find the slope of this line. To do that, we need to find its rise and we need to find its run. So as always, right, try to find good points where you don't have to estimate too much. Like, I see that one. That looks pretty good. It's right at an intersection. I won't have to estimate where it's at. And then I'm just looking for another one. Ooh, that one's pretty good too. Okay, so I'm going to use those 2 points to figure out how much my graph runs and rises. So here we go. So it looks like it runs from 35 to 90, right? So my run is going to be 90 inverse meters squared minus 30 inverse meters squared, or 60 inverse squared meters, okay? And my rise looks like it goes from here, so that would be 25 plus 6.25, right? If this is 12.5, then half of it is 6.25. So this is from 31.25 up to 81.25, right? Of course, you could always fill these in if you're having a hard time with that math, right? But again, every 4 was 25, so every 2 was half of that, 12.5, and then half of 12.5 would be 6.25. All right, so anyway, my rise here would be 81.25 millinewtons per coulomb. So I got to be careful there, right? Don't want to get myself in trouble. These are millinewtons per coulomb. So I'll need to make sure I convert those to newtons per coulomb before all is said and done, and I'm actually doing the math, okay? Minus 31.25 millinewtons per coulomb. So we get that the rise is 50 millinewtons per coulomb. And before I forget, I'm just going to go ahead and say, okay, 50 millinewtons, remember, milli from the back of your formula sheet just means 1/1000th, right? Or 50 times 10 to the minus 3 newtons per coulomb. Okay, so we did it. We've got our rise, we've got our run. All that's left to do is use the equation we derived using graphical analysis. Again, right? We're not guessing. We didn't guess it was the slope. The equation tells us it's the slope if we just look at it and, let it tell us what we're doing with y and x. Okay, so that means our slope, let's just get our slope, and then we'll divide it by Coulomb's constant, K. So slope is rise over run. And we've just worked out that the rise is 50 times 10 to the negative 3 newtons per coulomb. And the run is 60 inverse meters squared, right? And therefore our slope is just going to be, right, 50 times 10 to the negative 3, or 0.05 divided by 60, which gave me 8.3333 repeating times 10 to the negative 4. Our units now would be newtons per coulomb, but then those are getting divided by meters to the minus 2. We could, if we wanted, bring those up and make them meters squared. Okay, in the numerator, dividing by meters to the minus 2 is same as multiplying by meters to the positive 2. But careful, sometimes a common student mistake here is to go all this way and then forget the last thing, right? We wanted the slope, but we wanted the slope divided by k to get q. Okay, so we're almost done. Then q, whoops, that's not a q, that's a g. Q will be our slope divided by Coulomb's constant, K. So it will be 8.3333 times 10 to the negative 4 newtons per coulomb, meters to the minus 2, over K, Coulomb's constant, which we always have, right? It's on the back of your formula sheet, 8.99 times 10 to the power of 9 Newton meters squared per coulomb squared. And moment of truth, that means the charge on this Van de Graaff generator must be, I got 9.2696 times 10 to the negative 14 coulombs. I'll talk about units in a second, okay? For sig digs here, I would probably honestly just match the data we were given, which was all given to 2 sig digs, since that data kind of determines how accurate and precise our experiment is anyway. It probably determines how accurate our result can be. So 9.3 times 10 to the negative 14 coulombs is our final answer. Really quick, let's just think about the units, because you might be looking at that and being like, how in the world does that come out to be coulombs? So let's just do a quick unit check. That's a nice way to check our work anyway, to see if what we did actually makes sense. So here's what we had, right? These were the units of our slope, and then we were dividing them by Coulomb's constant, which has these units, right? So does that actually work out to give us coulombs? Well, I'm dividing by a fraction, so let me just rewrite that as multiplying by the reciprocal. That's kind of usually easier to think about. So I'm going to multiply this by coulombs squared over newtons meters squared, right? Dividing by this fraction is the same as multiplying by its reciprocal. And then this is already looking pretty promising, because once I multiply these together, I'll have newtons coulombs squared over coulombs times meters to the minus 2 times newtons times meters to the positive 2. And look at all this cancellation. Newtons over newtons is just 1, right? Coulombs squared over coulombs, well, coulombs squared is coulombs times coulombs, so one of those can cancel out. And then meters to the minus 2 times meters squared, right? We know that's from our exponent laws in math, right? Meters to the minus 2 times meters squared, that's the same as meters to the negative 2 plus 2, which is meters to the 0, and anything to the power of 0 is 1. So those actually cancel out as well. So we're just left with units of coulombs. And now we're feeling pretty good, because at least our answer had the right units, right? We must have done something algebraically correct, okay? So I feel pretty good about that. All right, now that wraps up chapter 11, lesson 1. Okay, so you are now, of course, you're good to go work on whatever practice questions you left for now. Okay, the remainder of the practice assignment that I gave can all be done for chapter 11, lesson 1. As always, right, if there's anything you're stuck on, anything you want to talk over, feel free to reach out. I'm always happy to help. Book a meeting, send an email, whatever it is. But yeah, there we go. 1 lesson down for chapter 11, 2 to go.